Hello, everyone. My name is Pablo Araya Araya. Yes, it's twice Arayas. So I'm a, as Arjun said yesterday, I'm a post pre-doc. I was here during the fall last year. And today I'm going to show my results for a paper in preparation. The title of this work is The Nature of Multi-Wavelength Detection of Proto-cluster of galaxies. And it's a simulated perspective of the galaxy population in these environments. So I didn't say, but I'm a PhD candidate at the University of São Paulo in Brazil, working with my advisor, Lars Soder Jr. And okay, so let's start talking about protoclusters. So those are defined as overdense regions at higher redshift that will evolve eventually into a galaxy cluster of redshift 0 or before. In that cartoon, we have like a illustration of what protoclusters are. Basically, are an ensemble of dark matter halos that will, as I said, evolve into a galaxy cluster at redshift 0. They, compared to their clusters, they occupy very large co-moving areas in the sky. Here we have like a measure of the sizes of protoclusters, I mean the radius. And we can see that at redshift 2, those protoclusters can have a size of about 8 co-moving megaparsecs. So they're pretty big structures. For example, clusters at redshift 0 are of size about 1 co-moving megaparsec, something like that. So to detect protocluster candidates, using observations, we search for overdensity of galaxies. So there are many techniques that depends on the available data that we have. Based on photometric bands, some of them are very efficient. In this case, in this work, they trace protoclusters using H-alpha meters that basically with a broad band and a narrow band, you select the galaxies that present an excess in H-alpha. So it's pretty efficient to select the galaxies that are at those redshifts. And we can see that we have some candidates searching for overdensity of this type of galaxies. Another galaxy population that are easy to select at high redshift are the Lyman break galaxies, as we need basically 3 broadbands in the optical, and trace the Lyman break, we can select galaxies at a certain redshift. Also, both that I mentioned before are in the optical, but in the 2 millimeter wavelength, the protocluster candidates, we detect them starting with observation with very low angular resolution of about, of about 1 arcmin. Then if we perform an observational follow-up with better angular resolution, we can see that point sources in low resolution 2 millimeter observation are basically composed by multiple sources and very small areas of about 100 of kiloparsecs. So this is a very famous protocluster, redshift 4.3, composed by 14 sources at that redshift that compose our protocluster core. So why do we find 2 millimeter sources, which are very rare objects in protoclusters? So in this work, I'm showing the star formation and stellar mass relation at 2 different redshifts. And those are galaxies that are pretty massive and are still in the main sequence. So those are the 2 millimeter galaxies. And since we expect in this environment to have more massive galaxies, for that reason, we expect to find 2 millimeter galaxies hereafter SMGs in protoclusters. So, but it's still in debate if protoclusters really are good traces of protoclusters. In this work from simulation in meters 2015, we can see that the overdensity traced by galaxies, for example, Lyman break galaxies, compared with the overdensity of dark matter, correlates pretty well, but it's not the case for SMGs, which is in the bottom panel. They're much more scattered. So in some cases, we can is not very correlated. For example, we can obtain a pretty large galaxy over density traced with SMGs, but not have over density of dark matter. And also in some cases, SMGs are not in the most massive dark matter halos in a certain redshift. So it's still in debate if those are good tracers, because it presents an incompleteness bias. Not all massive dark matter halos host even a single SMG. On the other hand, in observations, there's a recent work of Calvi 20 of this year, actually, that showed that 11 out of 12 SMGs are in overdense regions. So it's still in debate if SMGs are good tracers or not of proto-clusters. So the question that I want to answer in this work are, using simulations, a simulated perspective, are SMGs common in proto-cluster region or not? Okay. Is there an environmental or epoch preference? I mean, redshift, or if are more common in cores or the outskirts of proto-clusters? And also, on our simulation context, because we depend on our model, what mechanisms trigger the submillimeter emission in proto-cluster galaxies? And so another question that we answer in the work is it easy to find an optical counterpart of SMGs? But given the time that I have, I won't talk about this in this presentation, but you can ask me later if you are interested. So the data that we use is 36 square degrees mock construct with the techniques that I developed in my master's work, in my 2021 paper. I used basically a millennium simulation, scale plan cosmology, plus the L galaxy semi-analytic model. So millennium is just a dark matter only simulation, and then we run L galaxies to populate those dark matter halos with galaxies. And the idea of the mock is to have a simulated data that try to emulate as much as possible observations. As we can see, it's like a icon and not a moving box in different snapshots. We try to construct a fake observation, automatic catalog, basically. So to emulate, to incorporate submillimeter emission in the mocks, we use Rachel-Cochrane scaling relation that basically we can obtain the submillimeter flux density from the global properties of the galaxies. In this case, are star formation rate, stellar mass, dust mass, and redshift. And I'm not proud of this plot. Is comparing the number counts, which is compared with observations. How many galaxies with a certain flux, submillimeter flux density we have per beam compared with observations. So we cannot match pretty well the observations, but this is still unsolved problem in the literature. Because to explain this is kind of difficult to self-consistent, obtain a model self-consistent with matching the number counts and the other sanity checks, for example, the quench fraction of galaxies and those kind of things. So, but we still, the shape are pretty similar, and we think that we can track the main trends, at least the trends. We don't trust much more in the numbers, but yes, in the trends that we obtain in the analysis that I'm going to show you now. So in the mock, we have structures, clusters, proto-clusters, and we define cluster as a friend-of-friend group with a dark matter halo with M200 higher than 10 to the 14 solar mass at a very redshift, and proto-cluster, the progenitors of those structures with the main dark matter halo have masses below that limit. And here we show, just to you have an idea, the distribution of this structure at different redshift. And I'm going to classify proto-cluster into three types: Fornax type, Virgo type, and Coma type, based on those range in the descendant mass, which is the final mass of the protoclusters. So I have some numbers here, and we separate the different environments in protoclusters. It's just a cartoon. We define the core as all galaxies that are in the most massive dark matter halo that compose the wall structure. We can see that not always coincides with the center of masses of the structure. And in the case of protocluster outskirts, we define them as all galaxies enclosed in a sphere of twice the effective radius defined with this equation, which is actually the same radius that I showed you in the introduction in my first plot. And the sphere center, in this case, in the center of mass of the structure. So this is the most important result that we obtain. Basically, for each structure in the mock, we quantify the fraction of SMGs compared with the total of galaxies in a given environment. And we track that quantity as a function of redshift. So we define SMG in the simulation as all those galaxies with flux density higher than 0.5 millijansky. This is as a function of redshift, as a function of the environment, and also in protocluster type. So the most remarkable trend is that protocluster core exhibit an enhancement of submillimeter sources, which also depend in redshift. This implies a submillimeter bright phase. At least most of protoclusters cores have at least one SMG. Host at least one SMG. Also, there is a peak and duration of this submillimeter phase, and also that present a clear dependence of the protocluster type. So for coma types protocluster, which are the progenitors of the most massive structures, the submillimeter phase and the peak start earlier compared to the other ones with lower mass. Also, protocluster outskirts galaxies present galaxies in the fraction of SMGs in the outskirts and the field are very comparable between them, are very similar. So why we obtain those? So what are the galaxy properties that generate this trend? So we analyze the distribution of stellar masses in each protocluster type, environment, and different redshift. And we can see that even at redshift 4 in the top, the bottom panel, protocluster core already hosts massive galaxies. So this is the main reason that we obtain those trends. And also, as we can see also in observations, here we analyze for each bin of stellar mass, we quantify the median star formation rate, and we compare those star formation rate in cores, outskirts, compared with the field main values, galaxies in the field. So if that quantity is 0, it implies that the galaxies in that specific environment and the stellar mass are close to the field values. So what I'm showing here in the core is that, as I showed you before, galaxies in the core are very massive, and given this plot, they are in the main sequence. They are not starburst galaxies that are crazy. They're not present a crazy star formation rate. They follow the main sequence, but these quantities are pretty high because they are already massive structures, galaxies. So just to conclude, given our simulation and dust emission modeling, we predict that SMGs are more likely to reside in protocluster cores, which experience a submillimeter phase. That depends on the protocluster type. Protocluster cores host SMGs due to an early evolution of these galaxies because they are already massive even at redshift 4. And since they belong in the massive end of the field main sequence, I mean, the star formation rate and the stellar mass relation, they are at the massive end of that relation. So this is a direct consequence of downsizing, that galaxies, massive galaxies form the bulk of the stars, stellar mass earlier compared with other galaxies. And also that I didn't show here, I didn't show you here, is that it's challenging to also find an optical counterpart of SMGs due to this obscuration. And that's it. Thank you.
Thank you very much, Pablo. Do we have any questions? And people on Zoom, please write any questions in the chat. I'll be monitoring that. So I had one question for you, Pablo. You mentioned this tension between the model and the field counts. Do you have any idea how that could be addressed?
That one. So you already know the answer, but so we are doing the following. So we use a semi-analytic model. A semi-analytic model is basically you put all the equation that domain the galaxy evolution and formation in a single code, and those equations have 3 parameters that you can constrain with using observations. So what we are trying to do is to constrain those values to also predict that number count. So this is a way that we could solve the under prediction of the number counts of SMGs. I don't know if we will have an answer or not, but at least we are trying to do that. And in particular, the model that I use, the L Galaxies semi-analytic model, has an option that you can perform an MCMC kind of mode to try to obtain the best fit of those 3 parameters in the equation.
Thanks. Please.
This is a really cool talk. Thank you, Pablo. I'm curious about, and you may not know this because this is with respect to the data, but those error bars look really, really tiny. Is there? So do we believe that the actual data are that precise, or do we think that we're maybe underestimating the size of those error bars?
So those error bars, I don't know, I'm not sure, but I think that are most related with the instrument errors more than other things. But since you need like so 2mm observations have like a very small field of view. So, and to try to find the sources, you need larger volumes and areas because are rare structures, right? So maybe there is a systematic related with the cosmic variance, something like that, but I'm not sure. That is not included in the error bars. But yeah, I think that the error bars are more related with the instrumental errors than other things.
Awesome. Thank you. Appreciate it.
Yeah, Shai?
Do you know if these massive galaxies in the proto-cluster cores have special formation histories? Or, so they lie on the main...
that, but I can check the star formation histories. It is an output of the L galaxy. So actually, I use the star formation history to drive to attribute to each galaxy an SED and then compute the optical magnitudes and those kind of things. So maybe I can check that. It's an interesting.
Okay, one final question, Priscilla.
Thanks for an awesome talk, Pablo. I was wondering what is like, so I would assume that if you're trying to find these submillimeter galaxies, like in observations, you would target known overdensities, right? Like Lyman alpha emission nebulae or something that we typically associate with a proto-cluster. How many SMGs would we actually expect to find? Like how many, I have no idea for how many we actually know, like observationally are out there versus how many you're finding around proto-clusters in your simulation.
So, can you repeat the question? I think that I...
So like so what is the feasibility of detecting them observationally? Like how many would we expect to find around a protocluster based off simulations, and how many do we actually see around like proto-clusters we've observed?
So I really don't know. I think that I haven't seen a paper talking about that, because it's kind of so we can try to have an answer with the mock, of course, but since we are under predicting the number counts, we cannot just in the number. I mean the fraction, the fraction of the real SMGs that are in proto-cluster and those kind of things. We cannot have an absolute number. So it's hard. Some people use just, I don't know, the integrated star formation rate in a certain area and then compare those with observation. And for example, observation from Planck, they have a catalog of compact sources that are likely to be proto-clusters. And I think that the completeness of that completeness that they obtain using that approach, using simulation 2, is like above 70%, something like that. But yeah, it's not, they don't implement the cuts in the flux density and those observational constraints, right? They use like an integrated star formation rate.
Good afternoon, everyone. My name is Shelley Jia Cheng, and I'm a third-year PhD candidate at Harvard. I'm also a pre-doc during this semester, working with Matteo Cantiello, who's wonderful. And I'm really excited to share a little bit about my work on estimating eruptive mass loss in massive stars with Mesa. The other collaborators on this project are Matthew Renzo, Jared Goldberg, and of course my advisor at Harvard, Charlie Conroy. So I'll start off with a little bit of background about why massive stars matter, right? So here on the left, I show Zeta Ophiuchi, which is a beautiful O-type star that is closest to us, actually. And you can see this wonderful bow shock feature, right? You know, the red here, right? And that's because the star is moving very, very fast through a region of the galaxy that's very dust rich. So massive stars are beautiful. That's one reason. However, for those interested in galaxies, compact objects, and supernovae who are in the room, massive stars are also important in those contexts. So for galaxies, we know massive stars changes the density and overall movement of matter in galaxies, which can change star formation and also star cluster formation. And obviously, stellar winds and feedback is very important in galaxies. And for those interested in compact objects and supernovae, mass loss of massive stars is also very important. So we know helium stars and the mass loss of these helium stars can actually constrain the masses of black holes and neutron stars, which we can then use to study gravitational wave sources. And for supernovae specifically, we know pre-brightening phases of type 2n supernovae are due to mass loss of massive stars. So the overall point here is that massive stars should be something we all care about, not just the stellar astrophysicists, you know. All right, so observationally, one type of massive star we observe are called red supergiants. And there's an interesting observational kind of limit that's been observed of 20 to 30 solar masses. So we don't really observe massive stars more massive than 20 to 30 solar masses that are red supergiants. So here I show a Hertzsprung-Russell diagram, HR diagram. I think some people are familiar with it, but some may not be. So it shows luminosity in units of solar luminosity on the log scale on the Y, and on the X is the effective temperature on a log scale, but like flipped. So lower temperature is on the right. And I showed two evolution tracks of two stars, one at 15 solar masses and one at 30 solar masses. And it starts from the start of main sequence and ends at the end of core helium depletion, right? And these are not isochrones. They're one single star evolving through time, right? And red supergiants populate this area of the HR diagram, and that's a very, very famous example that we may all know. It's Betelgeuse, which may or may not go supernovae in the near or distant future. And yeah, so observers have actually been able to, see these stars, but interestingly, we don't really get them above 20 to 30 solar masses. And the postulated idea for this is that there's some post-main sequence mass loss that prevents the stars from evolving and cooling to become a red supergiant. But again, theoretically, it's not very well studied or well understood. If we move to higher masses, we actually become luminous and blue and variable. So luminous blue variables, and they exhibit eruptive mass loss. So here I show the same diagram, HR diagram, but now you may notice there's 3 additional tracks. So there's quiescent LBVs and LBVs in outburst. So these are the luminous blue variables that either are or are not erupting. And there's also in red the Humphrey-Davidson limit, which can be interpreted as the Eddington limit for stars. So this also may be familiar, but also may not be. So Eddington limit is when the gravitational force is balanced with the radiation pressure force outwards, right? And that observational empirical red line can be associated to that. So again, I want to emphasize these three lines are empirical kind of observations. So in observational data, they found stars that kind of form these tracks, right? And a famous example of LBV is AG-Carinae, which is this beautiful star here. And I want to emphasize this is a star. This is not a supernova. There's still a star there, despite a huge shell of material around it, right? And based on the distance of the shell, as well as the integrated light of the shell, observations have been able to constrain a mass loss rate of a very high rate of 0.1 to up to a few solar masses per year. And that's incredibly high. And it only lasts around 10 years. So this is an incredible kind of eruptive mass loss kind of behavior, right? So that's why it's called eruptive mass loss. And one thing to remember here is that this type of mass loss, again, is not really well understood by theory. And to really fully study these stars, one really needs 3D simulations. And some work has gone into these 3D simulations by Yangfei Zhang here at the CCA in this 2018 Nature paper. So here, the center of the star is at the very bottom where the 10R sun symbol is. And I show here the gas density on the left and the radiation energy density on the right. One thing to note is that in the pinkish region on the left, you actually can see some turbulence starting to occur, right? And this is a 3D simulation of a sliced wedge of the star, right? And you note that the photosphere, in the purple region, there's big plumes that occur, right? So it's a very not spherically symmetric system in 3D. And the main conclusion in these 3D simulations is that helium opacity peaks in the atmosphere can drive mass loss. And these opacity peaks occur in the purplish region where the temperatures are cool enough for helium to recombine. And these 3D simulations are wonderful, very informative. They allow us to derive a mass loss rate. However, they're incredibly expensive computationally. So for 3 individual snapshots in time in the HR diagram, it used 60 million CPU hours. So that's 3 moments in time on the HR diagram, and that's very expensive. So if you want to study a single star through its entire evolution, or multiple stars throughout their whole lifetime, you ultimately need 1D modeling or lower dimensional modeling. And that motivates our research questions. So firstly, how can we actually understand eruptive mass loss in massive stars in 1 dimension? And can we estimate a mass loss rate for massive stars using 1-dimensional models, right? The main tool for this is something called Mesa, so modules for experiments in stellar astrophysics. And this code is very sophisticated. It has all these ingredients of stellar structure equations, convection, microphysics, and there's also additional physics such as diffusion, mass changes, and rotation. In our study, we're focusing on stars of masses 10 to 100 solar masses, of metallicities 0.001 to 1 solar metallicity. The simulations I'll show in the next few plots will focus on 1 solar metallicity and will run lower metallicity in the future. So now we're looking at mass loss, right? Mass loss is what we're interested in. And we have to understand in a star, there's 2 kinds of mass loss happening at the same time. The first type is a continuous wind. So this occurs throughout the evolution and has a lower mass loss rate. And the second type is that eruptive mass loss that I've shown in this AG-Carinae system. And that only really occurs throughout part of the evolution and has much higher mass loss rate. So there's 2 things happening at once concurrently. The first type has been well studied already. The first type here in the Mesa code is called the Dutch wind, or the authors are from the Netherlands. And the m.Dutch, the mass loss rate, actually depends on a lot of variables: metallicity, mass, luminosity, effective temperature. And this model captures a line-driving wind mechanism. So what is a line-driven wind? This schematic shows that. So in the stellar atmosphere, I have a photon that hits a metallic ion, and that ion can either scatter it or absorb and re-emit it. In the process, it gains some momentum, and then it can collisionally couple to a hydrogen or helium atom in the atmosphere and drag it out. So this is line-driven winds. Basically, light hitting metallic ions and dragging helium hydrogen along with it. Right, so this is well studied, well understood. However, for eruptive mass loss, there is no theory for it at this stage. And To explain this, I'll first explain a little bit about how energy is transported through a star. There's two ways. It's either through radiative diffusion or convection. So convection, we probably all know, is water boiling, basically large movements of fluid. It rises and cools, then it sinks and heats up, cycles of that. Radiative diffusion is when a single photon carries the energy through almost like a random walk. It bumps into things and makes its way out. Convection tends to trap things. Radiative diffusion gives a chance of things to make it outside of the star. So if we want mass loss, radiative diffusion is what must carry our energy. Now I show a plot. We're going to break it down slowly. So on the x-axis, the surface is on the left and the core is on the right, and it's log of temperature. So the surface is lower in temperature on the left. On the y-axis, I show a ratio between a luminosity and the Eddington luminosity. So I mentioned previously, Eddington luminosity is when the force of gravity is balanced with radiation pressure. And the numerator luminosity can either be total, which is in purple, radiative in green, or convective in blue. By radiative and convective, I mean the luminosity carried by radiative diffusion or convection. And the red dotted line here separates regions of the star where diffusion occurs and dominates versus where convection occurs. So towards the left of the red line is where radiative diffusion can actually carry energy, and towards the right, convection is very efficient and traps energy. The black dotted line is when the ratio is 1. So anything above the black line is locally super Eddington, and anything left of the red line can be transported by radiative diffusion. So if we want mass loss, we're looking at this region, right? It has to have more luminosity than necessary than the editing luminosity. And in terms of radiative diffusion or convection, the energy has to be carried by radiative diffusion. So formally, I'm going to define this critical optical depth in red as C over V sound. So can a photon make it out? And for my energy, I'm looking at this excess luminosity, so the locally super Eddington luminosity, paired with some timescale, in this case, the dynamical timescale. And I'm going to compare that energy with the binding energy of the envelope, right? If it exceeds the binding energy, ideally, we're ejecting the mass. And this mass loss rate, again, involves a dynamical time. And then now I have this curly E Greek xi letter, which is an efficiency factor. So why do I have this efficiency factor? This is because this dynamical time is the shortest timescale for anything to really happen in a star. So this kind of overestimates the mass loss we will get. So this xi factor allows us to tune our model, and actually xi will be less than 1. Right? So this is this eruptive mass loss model. It's an energy argument in its very basic form. So throughout the evolution, these two different mass loss mechanisms occurs at the same time. So here I show an M equals 30 solar mass model. On the left plot here, I show solar mass per year, so mass loss rate, over age. And on the right, I show an HR diagram of the same star. And everything in black is that continuous line-driven Dutch wind model. And everything in the red is that eruptive mass loss model that I just talked about. And I note on the right, the black line actually extends underneath the red as well. So you'll notice here that, again, the black occurs throughout the evolution, whereas the red only really occurs in a specific region of the HR diagram in specific moments in time. In this case, it dominates, right? So before I present my preliminary results, I'm going to show the plot I'll be plotting my results on. Again, it's the HR diagram with those 3 empirical tracks. But now I have much more gray evolution tracks, going from 10 solar mass all the way to 100 solar masses, right? I'm only showing every 5 solar masses, but I did actually run models at every single incremental solar mass, so 11, 12, 13, etc. So now I will show the calculation results of my eruptive mass loss model here. So it's actually shown in that colored contour. So the contours, the colors show the logarithm of the eruptive mass loss model in units of solar masses per year. And I want to emphasize here that now the gray tracks are still evolving only using the continuous wind model, but I'm just calculating what would the eruptive mass loss model be, right? And you might note here that it occurs along this very thin sliver on the HR diagram vertically between 3.5 and 4 log T effective, right? And that happens to coincide to the temperature where helium recombination occurs. So this, in some ways, reproduces that 3D result that Yangfei 2018's Nature paper showed, where helium opacity peak is the reason for the mass loss. So that's great. However, what's more interesting is to see what happens if I actually evolve my stars using this eruptive mass loss model in addition to the wind, right? And now I show that. Let's focus on the left here, right? Left is when my efficiency factor is only 0.01. So I'm only operating at 1% of that eruptive mass loss model I showed. And here you can see all the gray lines still evolve. At this point, I will point at something. Okay, so I've never done this before. So here you actually see my stars, 35 solar masses evolves, it does become a red supergiant, right? You see the tracks here in gray actually survives, right? However, if I move my efficiency higher, I don't get that anymore, right? I'm actually losing my red supergiants above 30, 25, 20 solar masses. And if you recall from the introduction, observationally, that has been observed. There's a lack of red supergiants above 20 to 30 solar masses. And so with an efficiency of 0.1, so 10% of the efficiency of my dynamical time mass loss model of eruptive mass loss, I do actually get a lack of red supergiants. So that is a reproduction of that result, or a possible motivating explanation for the result. However, this could be a red herring, of course. We never know. And it could also be a red supergiant herring since we're missing supergiants. So in the end, what we can say is that, firstly, eruptive mass loss can be estimated using 1D Mesa. And then secondly, qualitative behavior agrees with the literature. So this is what I mean by agree. I'm getting a lack of red supergiants, right? And quantitatively, we can calibrate our results using that squiggly xi symbol. If we go back, you may note a star appeared, right? Do you see the star? So that star is a very recent development as of yesterday. Jared Goldberg, who may be in the room, not really sure, he kindly shared with me the result of a wonderful 3D simulation, I emphasize 3D, that has a mass loss rate of around 1 to the -6, and is at that point in the HI diagram. And you may notice the color of the stars close to the color of the background contours. So I think this is quite a positive result in the sense that I have one data point in 3D that agrees with what I have done in 1D. Just one. I think there'd be more data points coming up depending on Jared and Yangfei's future work, which I'm looking forward to use to compare with my simple 1D model. Yeah. So yeah, in terms of future work, I'll be tuning that efficiency factor, the xi squiggly symbol. I'll be evolving my models further all the way onto a core carbon depletion just to make sure we're being rigorous. And finally, I'll be running resolution tests to make sure it is not a red supergiant herring. And thank you very much for listening to my talk.
Thanks very much, Shelley. We have time for questions. Please. Sorry, can you use your C mic? Just press the button, wait till it's green.
Yes, it should be green now. Great talk, Shelley. Question about your tuning of the efficiency factor. Do you have a feeling about how you want to tune it? Because it sounds a bit like somewhat of a fudge factor that you're like playing around with, and it could even be mass dependent, right? So, like, do you want to compare this to 3D simulations? Are you just gonna move them around a bit more, or like, what are your?
Yeah. Okay. So firstly, I will look for different stars I can add to this plot. Thank you, Jared and Yangfei. So 3D simulations. I'll look at 3D simulations. In addition to that, my advisor at Harvard, Charlie Conroy, is really good at studying observations in stellar populations. So there is a pathway of looking at observational data and trying to get a total mass loss rate or instantaneous mass loss rate from that to compare, but that is a more nuanced process. So yeah, both observations as well as 3D modeling will be used to tune that efficiency factor. Yeah. Sure.
Hi, nice talk. Do you have a sense how metallicity will change this picture?
Yeah, so with metallicity, x plus y plus z equals to 1, right? So if I decrease my metallicity, my x and y increase relatively, and this is a helium opacity peak dependent thing. So one would expect the helium effects to be more dominant. So you may have a higher mass loss rate. Yeah. Yeah, that's just the first order expectation. Yeah. Sure.
Final question.
Yeah. With your model, could you learn something about the statistics of the eruptive events? Like, is it dominated by just a few really large ones or lots of smaller ones?
Yeah, so unfortunately, given it's 1D and real stars are not spheres of complete symmetry or lines, it's a bit hard to make conclusions about that. However, I will be doing 3D studies in the future. That is the plan, where this is acting more as a way to probe the parameter space, right? And that I can choose specific systems that are promising to study in 3D, after which I will be able to answer that question. So that is a goal of the project, yeah. Thank you, Vladimir.
Hi, everyone. I'm Nathalie Desante. I'm a fourth-year PhD student at the University of São Paulo, Brazil, and here I'm working as a pre-doc with Paco. And today I will talk about how to do cosmology with field-level likelihood of inference, trying to give the first steps towards working with real data. So we can start this presentation asking the question, is there an optimal way to do parameter inference? And we actually know that we can do this, for instance, using a summary statistics, the power spectrum. However, this is really good to deal with Gaussian fields, but it has some problems with nonlinear scales. Then we have to cut, we have a cut-on scale. So when we go to use, for instance, other machine learning techniques, we still have to grid our data, and then we have to choose a size for the small cells in this box. So unfortunately, we still don't have a good way to answer this question. So what we're trying to do here is proposing how to do galaxy field level likelihood for inference. So how can we extract all the information for a bunch of galaxies? The way that we are doing this is that we are translating all these galaxies and all this information in something that we call as graphs, which is a mathematical structure which contains and which can be a natural representation of the cosmic web, because we're tracing all the structure for these galaxies. So we are feeding our black box of machine learning, which are the graph neural networks, and which are pretty good to deal with regular data. And then we are estimating a megamatter. And this is a really good way to do this because, of course, after having the machine learning model trained, we can obtain estimations for the megamatter in a way which is really fast. And then we do not have to impose any cut-on scale. Another really important question here is, can we have a robust model? So we actually know that to train a machine learning model, we have to choose the data set. And then if we have a good model, it's supposed to get good predictions. The problem is when we try to change the data set in question and try to do good inferences. Most of the times we have difference in the data sets, which imply that we are not able to do this. But here, when we look for a robust model, we would like to have good predictions. And this is a really important question because we have like many different hydrodynamic simulations, for example, but we have only one universe. And if we can extrapolate and do predictions for everything that we know, possibly we can do this for the real data. Oh, it's working. Oh, sorry, because I was warned before that maybe this video was not working, but it is working. So in this video, which was made by Paco, we can see like 4 different hydrodynamical simulations. You can see Illustration G, Simba, Magneticum, and Astrid. And on blue, you can see the evolution for gas density, and on red, the evolution for gas temperature. And just by eye, even though these simulations are built in the way that they are supposed to be the same, for like while we are evolving in the redshift, we can see that they are at least by eye different. And is that possible that we can develop a machine learning model that can overcome all these differences? So let's look for this robust model. Oh, yeah, here's just like a picture of the final snapshot, just in case it doesn't work. So, and then let's talk a bit more about graphs. Unfortunately, I don't have time to go in all the details, but the main idea that I would like to say about graphs are that graphs are these mathematical structures composed by nodes, edges, and then we have the final graph right there, which can be described by 3 numbers. So the node attributes, the edges attributes, and then a global property for the graph. So in this work, we are taking into account our nodes as galaxies and as node attributes, the galaxy properties. Because we would like to work with real data in the future, we are taking into account for the best model only the z component of the velocity, and only one component, because in the real world we have only the velocity at the line of sight. The edges, we are determining then taking into account the position of the galaxies, and then we are considering the edge attributes just to take into account translational and rotational symmetries. So our global property are the number of galaxies. And then each one of these galaxy catalogs are going to be a graph for us that you can see this pictorial version right there. So let's talk a bit about graph neural networks, what they are. And then, as I told you, we are feeding this black box of machine learning with these graphs. And let's say that we are using our implementation for our graph neural networks is called message passing scheme, which means that we have blocks behind this black box, which are supposed to update the values for the node and for the edge attributes. And after many layers, we have a final representation of this graph, which contains all information related to small and larger scales. And at the end of the day, we're compressing all this information one more time in the way that we pass all this information through a simple multi-layer perceptron. And we are able to obtain the first and the second moment for the posterior distribution of omega matter. So the data set that we are using here are the Canon simulations. Yes, that's a Canon. And then these are really amazing simulations that we can vary many cosmological and astrophysical parameters. But to have this bunch of simulations, they are pretty small boxes, so only 25 megaparsecs. In these boxes, we have variations for two cosmological parameters, omega matter and sigma h. And then we have variations for astrophysical parameters to relate it to supernova and to relate it to AGN feedback. The data set, the set that we are using to train the machine learning model here is the L8 set, which follows for Latin hypercube, where we are able to vary all these 6 parameters here, varying the different random seeds as well. We are using this set to train the machine in the way that we are marginalizing over the astrophysical parameters. And then we have different subgrid physics models. We have Astrid, we have Lustrous-NG, we have Magneticum, we have Simba, SB28, and Swift Eagle. And then we can say, and we can highlight the fact that SB28 is not a new simulation. It's nothing more, nothing less than the same Lustrous-NG, but varying many other parameters. So we are varying 23 astrophysical parameters and 5 cosmological parameters. And then in Swift Eagle, this is a bit different because we are using another way to find these halos and subhalo structures, which is like Velociraptor. In all these others, the halos and subhalo structures are found using subfind. So that's it. In this work, we found the best model to work with to extract, to have good predictions for omega matter. And then we are using to extract good predictions for omega matter only the galaxy position, 3D positions, and the z component of the velocities. The training set that we are using to achieve this best model is Astrid. And then we are testing this machine learning model in these different hydrodynamical simulations. And the good news is that this works. And if you want to take a look at more details about this work, you can go to arXiv, or it's going to be on APJ soon. So here we have a summary of this work, and you are taking a look at truth minus inference for values for omega matter, per values of omega matter, per the true values for omega matter. On the top, you can see the predictions related to boxes for Astrid, so boxes that the model has never seen before while being trained. And then you can see that we have good predictions, so we pass it through the sanity check. And then the important thing here is try to take a look at what is going on with the predictions for these other simulations. And as you can see, just by we are following this 0 for all these different simulations, all the metrics are okay as well. And then we finally had a model which is robust, which can extrapolate over all these different hydrodynamical simulations. And this was the first time that we achieved a model like this. So the highlights that I would like to say here are first that this model is able to extrapolate for SB28. And remember, the model was trained on Astrid. So the model has never seen variations for these other 20 22 parameters. And then like the model is able to do these extrapolations for this as well. And then we can highlight the predictions for Swift Eagle. And then this is working even when we change the way that we're finding the halos and subhalos. So we found other things which was pretty important, that we can have a really good model for asteroid. And we took a look at the number of galaxies per box. So each point here corresponded to one simulation box. And then we can see that the model which works better while trying to extrapolate for all the others contain boxes which contains from tens of more than 5,000 galaxies, while a model trained on Sigma or Lucid G has never seen boxes with this kind of number of galaxies, and then this is not so good. So another thing is that asteroids contains variations in another galaxy properties, which is good as well for machine learning for the machine learning point of view. And that's it. So we can go as crazy as possible to get good models. But this was the first part. Now, and for the last months, we have been paying attention on new questions. The first question is like, okay, it works. We only need galaxy position and velocities, and we are working with peculiar velocities. But we know that in the real world, we have errors in the peculiar velocities. So is that possible that this model can take into account errors in the peculiar velocities? The way that we are incorporating this is like we are changing the velocity in the Z component for each galaxy in the way that we're taking into account a variation for 15 or 25% of this value, putting a Gaussian just to randomize the value that we're perturbing. And then we are taking a look, okay, let's see if the model trained considering all the galaxies without any error in the velocities is working. So all the plots that we're going to see on the left correspond to the best model applied in these catalogs. And all the results that will see on the right corresponds to a new model trained already using this difference in the velocities. So that's what I'm trying to say by left and right plots. Here, you can see estimatives for, like each point here corresponds to the average of the predictions for thousands of boxes for the different hydrodynamical simulations. And then you can see perturbations corresponding to 15% of the velocity on the bottoms that we have on the top, and 25% on the velocities that we have on the bottom plots. And then you can see, okay, our model can kind of deal with this, but when we retrain the machine learning, considering these variations for the velocities, we get good predictions. And the good predictions follows mainly for only or something around 15%. Okay, but in the real world, we have more than only errors in the peculiar velocities. We know that in real surveys, we cannot see all the galaxies. So we have things happening like we have bright stars that we have to remove. And when we do this, we are masking these stars from the surveys. And while we do this, we usually lost something around 5 or 10% of the observations. Okay, how we can deal with this? Let's see what our model can predict for our hydrodynamical boxes, removing 5 or 10% of the galaxies, randomly speaking. And one more time, our best model, and then our new models trained considering this randomization taken into account. So you can see that, okay, our best model trained with all the galaxies kind of works, considering this remotion of 5 or 10% of the galaxies. However, one more time, when we retrain the model considering these new galaxies, when we remove these galaxies, these models are better. And especially, this is even worse for Magneticum, but when we retrain the model, the results are better. Okay, but we don't have only these. We have much more. And for instance, we can split populations of the galaxies in galaxies which have star-forming galaxies or don't have this. What's going on? So one more time, we can do this split and take a look and see that, okay, our model can handle with this, but it's better while we are considering the new models, considering already catalogs with these selections. And then, okay, we can split the galaxies into blue or red galaxies. And here, it's really nice to see what is going on. Because with the GNNs, we can ask ourselves if we do have, if we're only measuring like properties related to clustering or number density. And then if we take a look at these two populations of galaxies, we can see if the model can handle with this difference in clustering. And so you can see that the best model is not so good to handle these differences. However, when you retrain the machine learning model, this can handle this. And then this indicates that the model is really, like the GNNs, are really taking a look into like clustering properties. So we would like to not stop there, and we ask ourselves, okay, we are only using hydrodynamical simulations, but because we would like to apply this to real world, we know that mocks are made with techniques, as Pablo told us, that are faster, okay? And then right now, we can show that this works for these semi-analytical models as well. Other thing that we can do and that we can ask ourselves is like, okay, it is general that we have like many different hydrodynamical simulations. We can see that, okay, we can vary only like 6 parameters, or we can go as crazy as possible and vary 28 parameters, as we do have in an SB28. So what happens if we train a machine learning model in Illustris NG and then testing all the others? Or if we go as crazy as possible and test and train our machine learning models in these craziest variations for varying all the 28 astrophysical and cosmological parameters. So here you can take a look at the predictions. On the left for the model trained on Illustris NG, and on the right for the model trained on SB28. And then you can say, oh, okay, Illustris NG is kind of doing a good job for extrapolating for Simba, okay, but it's not working so well for Astrid. And yeah, it does not work at all for Magneticum. However, when we have a data set which goes a bit more like crazy, we can see that, okay, we are doing a good job trying to extrapolate for Astrid, but we still don't have good predictions for Magneticum. So maybe like going as crazy as possible is not like only the good answer. We have to have models which take into account many other variations. For instance, Astrid, which takes into account variations in the galaxy properties, which Illustris NG does not take into consideration. So this is the most important graph that you can see in this presentation. So of course, in science, a work is not a work for one person. It's a work that everyone contributes to do. And there are many other people which are amazing and which contributed for this work, which are not here, but these are the ones that I'm highlighting. So thanks a lot. Thanks mostly to Paco. And then these are like the takeaway messages for this work, and then the next steps. So for the first time, we can do cosmology with graph neural networks using only galaxy positions and velocities. Nice. Our model is able to extrapolate for many other hydrodynamical simulations, for semi-analytical models as well. Our model can handle perturbations and velocities, can handle selections to color, star forming, and mask selections. And then, wow, we are giving the first steps to try to convince people to use these in real data. Next steps, of course, we do have them. First, we can try to take a look at other ways to go to things like to try to change these catalogs and train another models to take another real-world questions or real-world problems into account. Of course, we have to see if this model is going to be able to handle another faster techniques to get halos and galaxy catalogs. So, for instance, subhalo abundance matching techniques or even catalogs made with HODs. The model needs to be proven to work on light cones, but we don't have this yet for hydrodynamic simulations. And then we have to train this machine learning model in like mocks that came from peculiar velocity surveys. Please, let's try to convince people from peculiar velocity surveys to have these mocks to train this machine learning model, but for different cosmologies. And then, of course, we can try to not using only moment neural networks to constrain omega matter, but we can go further and try to use, for instance, normalizing flows or any other techniques. So these are the main questions that I was interested in this time here. Thanks.
Thanks, Natalie. So we have time for maybe one quick question, the remaining minute.
Sorry.
No worries. Please, Anthony. Oh, sorry. Yeah, go ahead, please.
So, great talk, Natalie. I'm interested, since you're now making the steps toward real data, there are obviously lots of spectroscopic data that'll be coming out with DESI and stuff that we have that's older from like BOSS and EBOSS. And then there are all the photometric samples. And when you think about photometric samples in particular, you tend to think of, greater uncertainties maybe in the photo Z or the N of Z distribution or anything else. So my question really is, when you start applying this to real data, do you plan to start with spectroscopy as a test bed and then build on? Or do you want to just go right to the photometry or some combination of the two?
So I don't know. Maybe we can try both. But before going there, we have to have a model trained on mocks for the surveys.
Right.
This is the first step. So yeah, I don't know the answer for this, but we are thinking about it.
All right, thank you for coming to the symposium, everyone. My name is Hannah Gerling Dunsmore. I am part of the spring cohort. I've been mentored by Rachel Somerville, Yanfei Jiang, and Uli Steinwandel. And today I'm going to present some preliminary results on a rapidly accreting supermassive black hole seed. There we go. So we have known for about 2 decades now through observational evidence that pretty much literally all galaxies host a supermassive black hole in their center. And if you point a telescope at the sky, about 99% of those galaxies are going to host what we call a quiescent galactic nucleus. That is to say, the supermassive black hole is not accreting significantly. It's certainly not accreting in a sustained way, and it's definitely not powering these powerful luminous outflows. That means that 1% of these galactic nuclei are what we call active, which is the opposite of what I just described. They are accreting significantly, it's sustained, and they are powering really, really luminous outflows, with the brightest of those being called quasars. And there was a time where people wondered, well, is there a fundamental difference between these 99% galaxies and these 1% galaxies? But we now believe that actually the picture is that in all galaxies, the supermassive black hole is active for approximately 1% of its lifetime and then quiescent for about 99% of its lifetime. And the reason why we believe that is that we can see the evidence of the coevolution of a supermassive black hole and its host galaxy on things such as the stellar formation rates, all of these sorts of things. We can see all this evidence. So we know that these are always have an active period. Now, before JWST, we were observing high redshift quasars at a redshift about 7, if you want to use round numbers, which means we had about a billion years to form them after the Big Bang. JWST has flown, it unfolded, it is taking data, it is wonderful, and it's also making our lives a little bit harder because now we have about 1/3 of that amount of time in order to form these galaxies. But you know what? Who's complaining about job security, right? There we go. Okay, I actually was able to figure out the clicker. Wonderful. So one question I get asked a lot is, why is it hard to grow a supermassive black hole? Isn't that the whole thing, that black holes, things fall into them and they can't escape? And that's true if you can get matter to the black hole, but the problem is getting matter there because these black holes are surrounded by accretion disks. And the accretion disks are really hard to make work, and they're hard to make work fast. Now, why are they hard to make work? Well, think back to freshman mechanics. You have something that's in orbit, and it's going to stay in, its orbital radius is going to be set by its kinetic energy, balanced by the gravitational potential. So you need to lose kinetic energy in order to move inwards. If you extend that to a continuous medium, like an accretion disk, what you have to do is move the angular momentum outwards so that the matter can move inwards. And that's actually harder than you would necessarily think to do. You also have to keep that disk stable. You have to keep it from fragmenting into stars. And that also is a non-trivial problem. Now, beyond that, if you start moving matter through these disks really fast, you start driving a lot more radiation physics in those disks, which that radiation physics in the classical picture should unbind in falling matter and slow down your accretion rate. So we're really not sure how they grow that fast and how they're able to power those luminous outflows. But the good news is that we have made substantial progress as a field. In 1973, Shakir and Senyaev introduced the alpha disk model, by which they proposed that angular momentum transport occurs due to this effective viscosity provided by turbulence within the disk, the strength of which can be parameterized by the alpha parameter, hence the name. In 1991, Balbus and Hawley showed that the magnetorotational instability can provide that effective viscosity. For those who aren't familiar, just a real quick explanation. You have a continuous medium differentially rotating. You send a magnetic field through it. Magnetic fields wiggle, and they get stretched apart. They get pulled together, and that can create, through various processes, angular momentum transport. And then finally, disk elevation has been proposed as a way to help keep these disks stable by Begelman and Pringle in 2007. And my primary thesis work is on the interaction of the MRI and self-gravity in the outer regions of a quasar disk. And I promise you will see why this is relevant in a few moments. And we are possibly seeing a novel disk elevating mechanism, but it's maybe not quite enough to suppress that fragmentation. And I do that work with Mitch Begelman, Phil Armitage, and Jake Simon. And this brings us to how do we try to make these disks work fast? So it turns out that the Eddington limit might be a little squishy. So Shelley Shang did a wonderful job of explaining the Eddington limit, so I'm just going to remind us really quick. The Eddington limit of luminosity is when you balance your radiative pressure with your gravitational binding energy of your object. And my slide seems to not be showing some special characters. It should say L equals epsilon times m dot, which is your mass accretion rate, times the speed of light squared. But it turns out that that radiative efficiency, and the epsilon parameterizes your radiative efficiency, and it turns out that that might not scale linearly. And you might actually get a turnover, as shown here in Inyoyoshi 2020, et al. 2020, where you actually get a turnover in that radiative efficiency. So that means you actually might be able to move things through the disk faster than you thought, which has created a lot of interest in the last decade or so in super and hyper Eddington accretion as a potential mechanism. Because at sufficiently high rates, you might actually be able to beat out those radiative outflows. And we now do believe that all supermassive black holes do need these really high rapid accretion periods in their lifetimes. Again, summarized really nicely in Inyoyoshi et al. 2020. So this brings us to the question that I've been investigating with Yanfei, Rachel, and Uli over the last 5 months, which is what happens with the radiation in the disks of these rapidly accreting supermassive black holes, and how does that impact the host galaxy as they co-evolve together in their early evolution? So we have been looking at connecting the galactic and horizon scale for black hole accretion. And this involves a few different things. First, looking at how the radiative outflows from this rapid accretion will affect the mid-disk and the outer disk. And when I say that, I mean the Keplerian region of the disk. We're not worried about relativity out here. And so we want to know, what are the inflow rates for getting bound to the disk? What are our inflow rates into the inner disk? Handing that off to the people who do worry about radiation, or relativity. I worry about radiation. And we also want to know what is getting ejected back into the galaxy to shape the evolution of the galaxy, which in turn also shapes what's available to be accreted. So our method of approach to look at this is we are using 2D radiation hydro simulations using Athena++. And importantly, we are using the implicit radiation implementation that Yanfei developed and is described in Jiang 2021. And in our initial study, we are looking at Bondi-like, what we call Bondi-like initial conditions. Bondi accretion is spherically symmetric accretion of a non-self-gravitating gas onto a compact object. And this was introduced by Bondi in 1952, hence the name. And the accretion rate developed from this, that you can derive from this, is given up here on the slide. And from that, you can go ahead and define a characteristic Bondi radius, which is where the escape velocity of that gas is going to be balanced by the sound speed of that gas. And you can go ahead, you can see this here. And in our study, because I know that Bondi radii are not what a lot of people are used to thinking of, so in our case, for our seed, it's approximately 10 to the 8 Schwarzschild radii. So here we go. This is the picture of what we're simulating, which is a 10 to the 5 solar mass supermassive black hole seed. It doesn't get to be a supermassive black hole until it's 10 to the 6. And it's accreting a few times the Eddington limit, about 5 times the Eddington limit. We are currently resolving 10 to the -4 Bondi radii up to 10 Bondi radii. And this is really exciting because this is a larger radial range than previous studies enabled by Yanfei's excellent implicit radiation implementation. We are using an alpha viscosity of 0.1, which is typical of a thin disk model. And we are modulating that by angle as was done in Hu et al. 2022. And we have a circularization radius set at 0.1 Bondi, which just basically means interior to that, it's a Keplerian disk exterior. Angular momentum is approximately constant. Now let's get to the good stuff. So first, on the left-hand side, we have pure hydro runs. There is no radiation in this run. There is radiation in that run. So it is a radiation hydro. And we will see, well, these are density profiles. They are angle averaged, and they look pretty similar. All right, well, that's not necessarily what you want to see when you're, controlling something. You'd like to see something change. So fortunately, we have our sound speed, first of all, to look at. Now, what the blue line is showing, well, the thick blue line, I also apologize for the not colorblind friendly colors. I tried to upload my own, and that wasn't working, so I apologize. But the thick blue line is showing the typical scaling relation between the sound speed and the radius of a disk for Bondi accretion. And you can see that we are matching that well. And you can right away see that there's a difference where in the case with radiation hydro, our sound speed is much more consistent through time, right? Whereas it has to get moving up to where the radiation hydro run ultimately ends up. So that's kind of interesting. All right. Now, here is our radial velocity profile. Again, I want to remind you that this is angle averaged, and this is normalized to the sound speed. And this is where we start seeing some real impacts of the radiation. So just checking to make sure there's plenty of time. So what we have here is you can see that initially in the pure hydro case, you have a much higher accretion rate, right? But that starts flattening out as the disk evolves. And that's what you would expect from Bondi accretion. And especially in Bondi accretion with a more simplistic, less physically motivated opacity, you would expect to see a lower accretion rate with the radiation physics turned on. However, we have a much better opacity, much more realistic opacity developed and formed by our enhanced understanding of radiation physics since the mid-19th century or 20th century. And we start seeing that, in fact, yes, we initially have a much lower accretion rate, that's true, but we are supersonic the entire time, and what's more, we don't get much, our radial velocity doesn't really get smaller over time. It is being sustained in the radiation case, and that is not what you would expect in the classical Bondi picture. That is interesting. I wonder what's happening there. How do I go ahead and make this press play? Okay, there we go, fantastic. So on the left-hand side, we have the density, the log of the density in CGS units. And on the right, we have the radial velocity of the gas in kilometers per second. And the first thing I want to talk about is, do I just press the green thing? Okay, there we go. And so the first thing you'll see is that our magnitude of our radial velocity is 5,000 kilometers per second. That is covering the entire United States in 1 second. And so the color bar is actually really, really apt. And this is the speed of supernova ejecta. And there we go. This is the speed of supernova ejecta. This is incredibly fast. And I'm hopefully going to be able to figure out how to pause this, because I want to point out some structure that if you've done accretion physics, you will recognize some structure here that I really want to point out, which is we are having these flows not coming through the midplane, but coming off midplane, almost as though evected. While we have our outflows. Oh, okay, cool. So can we press play? And then I'll let you know. Yeah, beautiful, pause. Thank you so much. So you can see that these are outflows in the midplane, and we have these and those are powerful outflows, and we can see that we have very rapid inflows almost being advected off of the midplane. Now, wonderful. Okay, and so now I want to quickly turn your attention to this density plot. Now, we can see here that as this is evolving, this might look a little familiar to some of you, which it's developing these tendrils that are really reminiscent of the Raleigh-Taylor instability. And in fact, people have found you can get Raleigh-Taylor developing in the presence and due to radiation, such as Jacquet and Krumholtz, 2011, Omer Blaze and Socrates, 2003. This is something that has been seen, and we may well be seeing this. Of course, this requires more due diligence, but it's very interesting, and it also would perhaps explain why we are sustaining that inflow rate, is that turbulence is driving that matter inwards. So this is very exciting, and I'm excited to look into this more. So future work, next steps. Of course, we have to do our due diligence. We have to keep comparing to pure hydro in a rigorous way. We need to run further diagnostics on the radiation physics to make sure they're doing what we think they're doing. And we need to, of course, do resolution tests because we don't want to make conclusions on numerical artifacts. We want to make conclusions on physics. We then want to explore interesting parameter spaces such as the black hole mass, the accretion rate, and our effective viscosity. And of course, radiation properties such as the number of frequencies that we are including, things like that. And then the step after that is to implement realistic initial conditions for galaxy evolution using simulations performed by Uli Steinwandel. So the implications of this. Now, I promised I would come back to my thesis work. I brought it up for a reason. One thing that's really exciting about this is that this can give us an idea of how much radiation energy is getting injected into the outer disk that might actually help figure out how do we keep these disks from getting truncated. Additionally, this is exciting for the inner disk because it helps provide more realistic inflow conditions so that they can improve their simulations. And of course, this has a lot of exciting implications for the evolution of galaxies, most notably the radiative outflows being injected into the galaxies. So very excited to see where this work ends up going. I have my summary slide up here. And I also would like to take a moment to, science is a team sport. And I, of course, want to thank my mentors, Rachel, Yanfei, Uli. Y'all have been amazing. Thank you so much for your help. And then I also want to thank Shelley Chang, Yori Devalar, Jared Goldberg, Mathieu Renzo, Jonathan Toshio, and Chris White for their additional help above and beyond, helping get these simulations working, helping get this analysis done. Thank you, everyone, and I'm excited for questions.
Thank you very much, Hannelore. Any questions? Please.
Okay. Thank you. Very amazing, interesting. I wanted to ask, what would you expect from exploring the other parameter spaces? For example, I have an impression alpha viscosity is the most uncertain and arbitrary thing.
So that's a great question. And I can honestly talk for 20 minutes just on that topic. So I'm going to try to focus that down. So of course, increasing your viscosity is going to change how well you can blow that material back, how well you can stir it. And so I'm really curious if this result holds up, that this sort of turbulence is helping maintain that inflow. How does that scale with viscosity? Is there a regime where that holds up? Is there a regime where that breaks down? So that's something I'm excited to see.
In the back, please.
Hey, great talk. I was just wondering, have you made a temperature plot of this?
I have indeed, and because this was, well, I found out that I had 20 minutes instead of 18, just a little bit before this talk. I did not include it.
Yeah, because I thought, it seems I was just curious if you get these kind of cavities where you have the low density hot stuff and then maybe cold thin shell around, kind of like the Andrew King kind of model.
Right, and that's a great question. And the only thing, I can't answer that because I've only done the radial profile so far. These results are literally just a few days ago. And so that's a great thing though. And that is something that I've been wanting to look into, is making a similar movie like this. Thank you.
We have one final question.
Really cool. Given your uncertainty in alpha viscosity, what are the prospects of doing this in MHD so you can have a self-consistent model for your angular momentum transport, as you explained so nicely with the MRI?
So bluntly, part of the constraint on doing that is the computational difficulty. That's going to be very expensive. So first, I think we want to narrow that parameter space down so we can really do that carefully. Now, what do I expect the effects to be? I'm going to be honest, I did not expect this. And so I'm still thinking about what that might look like. But, you know, this idea of stirring, I think the really exciting thing is more looking at how the effective heating both from the MRI and from the radiation might combine to shape broader scale physics. I'm not quite sure how to, I don't have a good intuition at this point of how the radiation will impact the MRI itself.
Hi, everyone. I'm Priscilla Olguin Luna. I am a PhD candidate at New Mexico State University. I'm working with Joe Burchett there. And my time here at the CCA has been spent working with Stephanie Tonneson and Shai Ganel, focusing on the CGM around satellites in TNG and tracking any stripping that might be occurring at the outer accretion shock in galaxy clusters. Let's talk about galaxies. So galaxies have gaseous halos, right? This is literally just the gas surrounding galaxies. We typically call this the circumgalactic medium, or CGM. And for a Milky Way-like galaxy, this is on the order of a few hundred kiloparsec. In a galaxy cluster, the gas that occupies the halo is called the intracluster medium, or ICM. And for a coma-like cluster, this is typically a few megaparsec in size. Now, this figure here from a recent review that's really wonderful is showing the CGM around a simulated galaxy. You can see there are a lot of outflows coming out above and below it. The cold gas is mapped by the blue and the hot gas by this yellow-gold color. And if this bottom panel right here is spanning 100 kiloparsec in size. If we zoom in, that very small point, we get to this top left panel, which is showing a cold cloud complex in what appears to be a hot cloud in the CGM. If we zoom in again one more time, we get to the actual turbulent mixing layer. So I want to point out that this figure here, this diagram, is spanning more than 10 to the 5 in scale. So we can't resolve all of the physics occurring at these different scales simultaneously. That's a very big limitation. However, everything that is occurring at these different scales is extremely important for the physics occurring at these scales is important for how galaxies evolve over cosmic time. So galaxy clusters occupy the most massive halos. We're talking greater than 10 to the 14 solar masses. And they've been typically studied in the X-ray. So this here is an optical image of my favorite galaxy cluster, Abell 1689. If I overlay the emission in X-ray, this is what that looks like. So the X-ray is tracing this very hot, dense 10 to the 7, 10 to the 8 gas in the core of the cluster. And I want to take a moment to define what I will call the virial radius. Throughout my work, this is R200C, so that's just the radius at which the density of the galaxy cluster, the ICM, is 200 times the critical density of the universe at the redshift of the cluster. I also want to define the outskirts of the cluster. So if we zoom out of this, you can see that there are still a lot of galaxies existing beyond the purple X-ray emission. And these are in the outskirts of the cluster. So this is beyond 2 to 3 R200C. I also want to mention the SZ effect, the Sunyaev-Zeldovich effect. This is the scattering of cosmic microwave background photons that encounter the very hot, dense gas in the core of a galaxy cluster. They get inverse Compton scattered, so to higher energies. And this is a way that we can actually observe galaxy clusters as well. We typically report this in terms of the Compton Y parameter, and I'll come back to that in a little bit. I just wanted to mention it here. So cluster satellites. This here is seminal work by Butcher and Omler showing that the amount of blue galaxies we see in clusters at higher redshift in earlier times, which is on the right of this plot, is higher than the amount of blue galaxies we find in clusters at later times and lower redshifts. So this is showing that the populations in galaxy clusters of satellites are different across cosmic time. There's also been this other seminal work by Dressler in 1980. This is the morphology density relation. So this top line here is showing you blue spiral galaxies. This middle one is S0, and this bottom one is elliptical galaxies. You can see that as the density of the environment increases, the density of the cluster increases, the amount of blue spirals is declining and the amount of S0 and ellipticals is increasing. So we would expect to find blue or star-forming galaxies in the less dense regions or the outskirts around clusters. I also want to talk about shocks in the cluster environment. This is another very important component of them. So this here is the gas entropy profile around a simulated cluster. There are two radii that are highlighted. The inner dashed line is the splashback radius. I'm not going to be talking about that at all. I just wanted to label it for you. We could chat about that later if you want. And this outer solid line is the accretion shock. So in a cluster, there are these internal virial shocks. These arise from merging within the cluster. So like an infalling satellite into the cluster core or filamentary structure that is penetrating the ICM and being accreted into the cluster as well. There's also an external accretion shock. So this is due to the infall of very low density gas from the surroundings. And this is actually a remnant of the first halo collapse of the galaxy cluster itself. So this is a probe of the mass assembly. So I want to just very briefly touch on results of this observational work I did prior to coming to the CCA, which has been a big motivation for my project here. This is work I've done. This is using quasar absorption line spectroscopy. If you have questions about any of the observations or anything, I'm happy to chat after about that. But I just want to focus on the main results of this. So DNDZ here is essentially a statistical, it's a way to show the statistically significant absorbers of H1 here within the redshift range over which they're detectable. So you could think of it as like the number of H1 absorbers that we've detected. And I have identified this excess between 2 and 3 R200. So the amount of H1 we're detecting within this range between 2 and 3 R200 is above what this black line is showing, which is the value we would expect to get. So what is that? We're like, what is this? What could this be arising from? So this here is some observational work from Elad Zinger. This is using TNG as well, TNG 100. And here is the radially averaged entropy profile for the same cluster at different redshifts. You can see that they've identified the location of the accretion shock or different shocks in the cluster environment, specifically for the accretion shock though. And if I overlay this excess region I've identified of H1, it actually is coincident with some of the shock locations in these clusters. If we look at some observational work as well, these are stacked SZ profiles. So this is what I was talking about earlier. This is the Compton Y parameter here, and the bottom is showing the pressure profile for these. You'll see that there are these two deficits in the pressure profile, and these are attributed in the paper to the location of shocks potentially. And if I convert our R200C to R200M and I plot it, the location of this excess of H1 I've identified that we believe may be attributed to the outer accretion shock lines up with the potential, with the deficit in the pressure profile that this paper is attributing to shocks as well. So another very important component of clusters or aspect of them is that they contain a very high amount of quenched galaxies. So it's known that there's a higher fraction of quenched galaxies in clusters. You can see here, this is work from Denari et al. The solid lines are from simulations from TNG 300, and the points are from SDSS observations. And the whole point of this is essentially just to show that cluster mass halos contain the highest amount of quenched galaxies. So this made me think, could the accretion shock somehow be a mechanism that's contributing to quenching in the cluster environment? Is there a relationship between those two? So my project here has been focusing on that. So let's talk a bit about the quenching mechanism, some of these potential quenching mechanisms. So first, there's starvation. which is essentially a slow, gradual cutoff of star formation due to the supply of cold gas running out. There's tidal stripping or harassment. This has to do with galaxies being disrupted due to tidal forces, either from galaxies interacting with each other or galaxy and cluster environment. Ram pressure stripping, which is the removal of gas, that could be the CGM gas or ISM gas, from a ram pressure force. So I like to think of like a dandelion. If you blow on a dandelion, you're applying a ram pressure force that's pulling those seeds away from it. In the same way, as a galaxy moves through the intracluster medium, that gas is pulled away by the ram pressure force of the ICM. There's also black hole feedback, which is a very general term, which refers to different physical phenomena that can contribute to quenching in a galaxy. And then I wanted to mention pre-processing, which is not necessarily a quenching mechanism. However, it refers to a process that, like galaxies, if they fall in a group, for example, into the cluster environment, they can be pre-processed in that they might experience tidal stripping or harassment and actually start to quench before they even fall into the cluster. So that is what pre-processing is referring to. So it's related to some of these. So how does the accretion shock fit into that? So the accretion shock, we believe, can be a cause of quenching and a point of reference to study these different quenching mechanisms. And it can do that by stripping the CGM and inducing starvation potentially, or stripping the ISM, causing rapid quenching to occur. It can compress gas, potentially induce black hole feedback, or by the same vein, compress the gas and potentially induce a starburst, which will then rapidly use up the gas. So this is the mass-weighted entropy profile for one of the clusters in my sample, which I'll talk about in a second. And this is how it changes over the redshift range through all the snapshots that we're tracking it. So my sample consists of 14 clusters in TNG 100. I have identified on the order of 25 to 100 subhalos per each cluster that I'm delving further into actively. That'll make up the actual tracked CGM sample. And we're looking at these subhalos we're tracking them from 0.5 to 0. So the first thing that I've done is identifying the accretion shock via this discontinuity in the entropy profile. You might remember this plot from earlier. This is showing that radially averaged entropy profile. This is typically how people identify the location of the accretion shock in simulated clusters. However, this is all the same cluster in different points of view. So in the x-plane, y-plane, and z-plane, you can see that radially averaging this might not be the best way to arrive with a single value for the location of the shock. So I really wanted to be very careful, especially because you can see that there's a lot of movement going on. I wanted to be very careful about identifying the shock location and identifying when a satellite is passing through it. So instead, what I've done is I've actually defined the entropy profile between each individual satellite and the core of the cluster for every single snapshot that we're tracking it through. So this here is showing one single galaxy. So this is all the same satellite, but this is the entropy profile across multiple snapshots. So going from pink here, you can see it hasn't entered the accretion shock yet. And this is entropy on the y-axis and just the impact parameter R over R200 on the x-axis. So as it gets closer towards the cluster core, you can see these values rising in entropy. These right here. So that is it encountering the accretion shock. That's it passing through the shock. So we have to do this on an individual subhalo basis for all of the satellites that I'm looking at around a given cluster. This is that same exact satellite that you just saw the entropy profile for, tracked across from 0.5 to 0. And you can see when it encounters the accretion shock. The subhalo position is this kind of star in a circle. So once I've identified the subhalos to track, I can track their CGM from their first infall to within the accretion shock. And this will allow us to identify if there's any stripping occurring, and if so, how much. So not only can we look at the CGM,
We can also compare this with other parameters that are potential indicators of quenching, such as a specific star formation rate and the black hole accretion rate. So on the top here, we have the CGM fraction. That is the CGM mass over the total mass for the galaxy. In the middle here, we have the specific star formation rate. And on the bottom here, we have the black hole accretion rate. So I've overlain this dotted line here at the location of the accretion shock. You can see that in the top panel, the CGM mass is declining a little bit. The star formation rate is ramping back up, and the black hole accretion rate's kind of just doing its thing repeatedly there. You might be like, well, what the heck? What about this thing? What's going on up here? There's obviously a larger dip in the CGM, a spike in the star formation rate, and this is a big spike in the black hole accretion rate. This galaxy in particular is actually a part of a group. It's a part of, there's 10 galaxies that are all falling in. So this could be pre-processing this potentially. We definitely need to look at this a lot more, but this could actually be evidence of pre-processing that's occurring and causing this initial decline in the CGM. Here's another subhalo around the same cluster. This is more along the lines, I think, of what the picture I've painted, where we see the CGM mass is actually rising, and then as soon as it encounters the accretion shock, it starts to plummet. So in summary, I have identified this excess of H1 observationally, right, between 2 and 3 R200 that we are attributing to the location of the accretion shock front. I have in TNG now began to track satellites across this accretion shock to identify if there's any stripping of the CGM. And I'm studying not only the CGM, but other parameters that could be indicators of quenching in context with it at the same time. And so our future work is going to include collecting, identifying control samples, so galaxies that aren't encountering the accretion shock for comparison, as well as accounting for pre-processing to make sure that we are that there isn't additional, an additional contributing factor to the quenching that's occurring, as well as potentially looking at radial gradients of the star formation in the ISM when these subhalos are going through the accretion shock to see if there's anything interesting happening there. So thank you so much for your time. I'm happy to take any questions.
Thank you very much, Priscilla. Questions? Please.
Is there a particular reason you don't consider lower mass clusters? Is that just because you can't really see SE observations for lower mass clusters?
So our cluster sample is defined at redshift 0, and the requirement for it is that the halo mass must be greater than 10 to the 14 solar masses at redshift 0. So that is kind of like it's a very loosely defined, kind of like some people are like 13.8 or 13.9 is the cluster, but we decided to just go with the full-on above 10 to the 14 solar masses as the definition of like what we're considering a cluster. Okay. So there is variance already like within that, right? As far as the mass of the halo goes. And so it'll be interesting, I think, to see how it differs for the different masses, especially since some of the clusters start off at much, much lower mass at the earlier redshifts. But once you start getting down into the group regime, the physics are a little different.
Thanks.
Questions? Please.
Great talk. Thank you so much. You mentioned the splashback radius at one point, and I'm curious about whether there's any relationship to where the H1 excess is with respect to the corresponding splashback radii.
Yeah, so that really depends on what work you're looking at. So the accretion shock is identified anywhere between like 1 and 5 R200C, depending on which simulation you're looking at. It's really kind of it's up in the air. The splashback radius, there was some great work by Ong et al. 2021. That's what that figure is from, actually. That quantifies like the location of the splashback radius in terms of the accretion shock. And so there's a relationship there. As far as you were asking the splashback radius relation to the CGM, right? Or like the stripping of
with respect to the H1 excess.
To the H1 excess. Yeah, so that's going to depend on what the accretion shock location is in a given work, unfortunately.
Yeah.
Hi, everyone. This is ironic because when I thought I would give the symposium talk, I thought I would be in person and the rest of my research group would be on Zoom, but now it's the other way around. And I find that kind of funny. So my name is Chris Lamb. I'm a fall semester pre-doc and a rising fourth-year grad student at the University of Florida. And my symposium talk is on the use of information theory to optimize the scheduling of radial velocity follow-up observations on planetary systems found by the transiting exoplanet survey satellite. So at the University of Florida, I work with Sarah Ballard, placing observational constraints on planetary dynamical evolution. But here at CCA, I've been working with Megan Bedell and Lily Zhao on using the Fisher information to optimize radial velocity follow-up to constrain planet masses. And the rest of my research group is also there. So that's me, that's Kadri Chance, former pre-doc, work with Dan Foreman-Mackey, Sheila Sager, current pre-doc, works with Adrian Price-Whelan and Natalia Guerrero. And they're all there right now. And so, yeah. Hi, guys. Okay, so this is Kepler and this is TESS, the Transiting Exoplanet Survey Satellite. Together, they found thousands of planets, and that's great. They've given us a lot of information based on multiplicity, the radius of planets, the spacing between planets. You can deduce a lot of information about planetary systems that way. One thing they don't give us, though, is the mass for that. Well, so yeah, one thing they don't give us is the mass. And we need the mass to answer a specific question that a lot of people ask, which is what are these planets made out of, their compositions. And so this plot, there's a lot going on. The best way to frame how to read this is just, so on the x-axis is the mass of the planet, y-axis is the radius of the planet, and these contours show you, what the bulk composition is of these planets. And so if you can imagine from these transit surveys, you get a good constraint on the radius, but you don't have a good constraint on the mass. You still can say if you have a radius of 2 Earth radii, there's so many different contours you could fall on depending on what mass regime you're in. And if you prefer argument, an argument that's based on just authority, it's also a level one mission requirement for TESS. So we find these masses using a technique called RVs. We don't have a lot of time to talk about RVs, so I'm just going to talk about them in the planetary context. And what RVs basically boil down to is using the Doppler effect to measure the wobble induced by a planet on its host star, and the size of that wobble is commensurate with the mass of that planet. So this is hard to disentangle because the star has RVs in its rotation, and the signal that you see in a star is much, much larger than the planet, as this plot shows. Now, you can decrease the error, the stellar variability with more, or the error from the stellar variability with more observations. And that's what a lot of people try to do. But you can begin to imagine that you're going to quickly reach a bottleneck where characterization of these thousands of planets that are obtained through these surveys is going to be a precious resource. Now, to illustrate this, we're going to take an example of a canonical young noisy star, AU-MIC. This has 3 planets. We're going to pretend for our case that we have just 1 planet around it. And then let's say I want to conduct a follow-up observation to estimate the mass of AU-MIC-B. So should I ask for once per night, 2, 3, 4, and so on? Should I ask for spread out observations that span the full observing semester? So say every other night could be 1, 2, 3. Or should I observe in intense bursts? So 1, 2, 3, 4, 5, 6, 7, 8, so on. And so there's several knobs that you can tune to construct observing strategies, and that affects the baseline, so the total time span from the first night of observation to the last night, as well as the placement of the gaps in these observations and the size of these gaps. And so this is a complicated but discrete parameter space. And the tool we use to compare these different strategies against each other is the Fisher information. Now, all that is it's a quantity that characterizes the expected value on the uncertainty of a measurement of a free parameter, of some given free parameter. Here, for us, it's the radial velocity semi-amplitude. And it has 3 ingredients. This is the equation for the Fisher information. And mu is the model. So for us, that's the Keplerian. Theta is the vector of planet parameter. So for us, it's the radial velocity semi-amplitude, the period of the planet, and the central transit crossing time. And then finally, big sigma is the covariance matrix, and that captures the parameters around the stellar noise. And we're going to see that later. So let's say you propose to observe 30 nights of AU-MIC-B, and you get these observations awarded to you by the Newitt spectrograph. So that's great. So now the question is, how do I spend this coin? And the first thing you would do in the pipeline, in this framework that we've created, is to feed in your stellar noise model parameters. And so the main ingredients here are your activity signal amplitude, your activity decay time scale. So how long-lived are your star spots? Your stellar rotation period. So how every so often does your star spot come back around? And finally, the complexity, the harmonic complexity of the star spots. This one's a little bit less physically motivated. But yeah, so that's the next step. And then you would feed in your planet parameters. So before we were feeding in our noise parameters, and now our the parameters for the model that we're, or the model with the parameter that we're trying to optimize our measurements for. So this is the Keplerian with the ingredients that I had listed before. And then finally, we produce plots like these for users, where the x-axis is the number of consecutive observing nights, and then the y-axis is the intentional observing gap. So 5, 1 would be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on. And so blue is good, yellow is bad. And yeah, so reading right off this list, you can pick a strategy that works for you, both in terms of the expected value on the uncertainty of your measurement, as well as, well, your practical, like, well, I don't want a baseline that spans, like, that will basically finish my campaign like 1 month or 2 months later than this other technique that perhaps maybe does a little bit worse. but like it's good enough. This basically gives users a principled way to make informed decisions. And we have a package. So it's on GitHub, but we also have a package out on PyPy, and it's called Gaspery. Okay, so that was a specific case, but there are some generic ground rules that we can also derive from this work. So these beautiful swoopy things are something called beat frequency. So the interplay between the observing cadence, the stellar rotation period, and the planet orbital period. So many timescales that interact with each other and produce these complex harmonics. And so the first case is actually not one of these circus tent swoopy things. It's the horizontal line. The plot on the right shows a phase folded RV curve where the blue dots is the putative planet signal, and then the red is both planet plus stellar variability when observed at the cadence that is given by the x-axis of the plot on the left. So these horizontal, if you're on a horizontal line, then you're in for a bad time because you're observing every planet orbital period, and so you're just going to get the same spot each time. You don't have good phase coverage, and so this is one way that a strategy can be bad. Another way that a strategy can be bad is if you're on one of these complex swoopy things, and this is where the value, I think, of Gaspery, of this work, comes in. That like this is less obvious and a little harder to compute, and so if you're on one of these lines, then you're also in for a bad time. Your expected value for your sigma k, your uncertainty on the radial velocity semi-amplitude that you observe, is similar to that when you like observe on these horizontal lines, which are a little bit more obvious to avoid. And then finally, this is an example, a trivial example kind of a good case that where you observe off of any of these blue high sigma k lines, and here you're observing every rotation period, and so of the star. And in this case, you've completely disentangled your stellar signal from your planet signal by choosing your observing cadence to be a very specific number. Okay, so we've produced a principled framework that allows us to see the interplay between stellar, planet, and observing timescales that can make it difficult to schedule observations to maximize the information content. We've produced a package in Python that can help you optimize your follow-up campaign. And this principled framework will enable more efficient follow-up in future science with tests and beyond. And so, yeah, I think I wrote these slides back when we had a lot less time, and I'll just leave it there because I think people want short presentations too sometimes. Okay, the end.
All right, thank you very much to Chris. And I'll just note, it's still 15 minutes. We just have more time for questions because we had a couple of people pull out. So don't feel you need to expand your talks at the last minute. It's totally fine. So any questions? Yeah, Adrian?
Hey, Chris. Thanks for the nice talk. So you focus mostly on the uncertainty in the semi-amplitude. What does it look like if you expand to look at the full covariance matrix of all the Keplerian parameters? Like if you don't have a good prior knowledge on the eccentricity, for example, what's the correlation structure look like?
Yeah, so right now our Keplerian model assumes a circular orbit, but the great thing, I did not mention this in this talk, but here at CCA, we worship at the altar of JAX, and this was implemented in JAX. So the great thing about that is the auto differentiation capabilities that JAX affords allows us to take the derivative, which is normally hard to analytically take, of an eccentric Keplerian. And so, yeah, this is something that we're going to hold in the future.
Awesome. Thanks.
Hello, my name is Eruptive. I'm a fourth year doctoral candidate in University of Turku in Finland. Here I'm a pre-doc this semester working with Jonas Nattila, who's not here now, and Vladimir Zdankin, who is here now. And I wanted to use this little opportunity to spread the word about plasma turbulence. And I guess actually in astrophysics probably turbulence does not need any spreading, because basically turbulence is almost everything that happens in astrophysics. Stars are like turbulent plasma, like everything in between. There's special cases that's especially interesting for us is when we have strong magnetic field that makes it all special when we have magnetized plasma turbulence, for example, in magnetars, in stellar coronae, in accretion disk around black holes or other compact objects, for example, in X-ray binaries or in active galactic nuclei. And as long as I am mostly interested in X-ray binaries, black hole X-ray binaries, I'm doing my PhD about observational properties of those. I will tell about magnetized turbulence in this context. So we have an X-ray binary, for example, Cygnus X1, and in the observed spectra, we see this feature that is called a power law tail on the right in the highest energies, and this is believed to be the consequence of some magnetized plasma turbulence that happen in the corona of the disk. By analogy with the solar corona, we have some magnetic loops that are boiling and floating above, and they also affect this low density medium right above the accretion disk. This is a turbulent process, and it is believed to energize the particles, electrons and positrons that exist in the corona above the accretion disk. And those electrons also energize photons to the higher energies. And we are very interested in those processes because this will get us better understanding of the physics of the accretion flow, because we only see spectra, but we don't know actually what's happening there. We only assume that these separate components, such as accretion disk, is probably this thing, and hot corona, this is this componized high energy thing, and also this power law tail. So we are interested in this non-thermal particle mechanisms because we want to understand accretion flows. Yeah, that's probably what I was just saying. And we, the mechanism of these non-thermal particle accelerations are not entirely clear. We only see that when we simulate when we simulate magnetized turbulence, we see those particles. So we assume, so we know it accelerates particles, but what is the exactly microphysics of that and what is the stages is not entirely clear. But of course, lately there was a lot of new discoveries in this field. So how do we study those magnetized turbulence while sitting in the room? Of course, by numerical simulations. I'm sorry. We use particle in cell simulations approach. It is very useful because it simulates the plasma from the first principles. So what is the basic components we have in our simulations is, of course, we have electric and magnetic field. Electric and magnetic field accelerate the particles. Electric and magnetic field exist on the grid, 3D grid, like different grids for electric and magnetic field, but it doesn't matter. We have fields on the grid. We have particles between grid running and traveling, and fields accelerate particles. Particle movement makes current. Current affects the fields, and so on and so forth in the circle. And so, how do we set up the turbulence? We have this box. This is a 2D box for simplicity, but the code is in 3D. The code is developed by Jonas, but I'm using it and trying to modify it. But more on that later. We have a box. Box is 2D. Fields are 3D. So we set up a magnetic field, which is very strong. More than this is parameter of the strength of the magnetic field, and it is 10. That means that the magnetic field energy is 10 times more than rest mass energy of the plasma. And we said this is constant magnetic field outside the plane, and we have x and y coordinate like magnetic field, some sort of harmonics up to, in this example, up to 8. But we have first several harmonics in the perturbation of the x and y magnetic field. Also, the size of those perturbations about the same order of magnitude as the z component of the magnetic field. And a couple of time iterations into the simulations, we see this map of the current. That means basically red and blue is different directions of the current out of the plane and in the plane, and it illustrates the direction of this magnetic field whirls. Where am I? Okay. This was the previous slide was showing sort of first 300 time steps, but all of the rest time steps. We see how turbulence is evolving. What we can see here. So in the beginning, it was like nice and clean, several harmonics, but now, further in time, we start to see all the different things. Those like circular structures are called plasmoids. In 3D, they would be like elongated in this sort of direction, but like of course in 3D they can be radiated anyway. And those stripes, the filaments that are called current sheets, it's like sheets when the current is directed predominantly one direction or another. So let's talk like more in detail what's happening here. Let's see, we have like two blobs somewhere in the plasma, and they're the same color. That means the current is directed the same direction. We know from school that we have ampere force from between those, so they want to hug each other. For example, let's look on those two brothers. They they attract, and in between we have this new thing that is called current sheet, and has the current opposite to the direction of this thing. And for example, if you see like some current sheet, for example, this one, what is happening here? We have two like same direction magnetic field lines. Well, they are of different direction here, but same direction in terms of like rotation. So and in between, it's not like one point. It's usually because of those magnetic lines are not that smooth. They're also turbulent. So we have multiple points where also magnetic reconnection can happen. So those fields are sort of like meet each other and form new structure. There's the plasmoids again, but on the smaller scale. So we see this zoom in of this thing, and boom, in 100 time steps, we already see like two new things. Those are going to break into new things. So we have all of that constitutes the thing that's called the turbulent cascade. So in the beginning, if we take the Fourier spectrum, spatial Fourier spectrum of the magnetic field, what I was mentioning in the beginning, we have only few harmonics in the beginning. So color is time, red color is 0 time, so we have it goes down, so we have nothing on those smaller scale. And as long as they collide and break and so on and so forth, we see how the power law emerges in this sort of picture, in this Fourier power spectrum. And what is important here that this describes our turbulence, but does not define our turbulence. Why do we run turbulence simulation in the first place if we know we can get this in the end? But actually, for example, I'm also not very proud of this picture, but this is not mine. So I'm going to probably make a better one in the future, but so far I only have this one for the illustration. Anyway, we have the same power spectrum for those two turbulence snapshot. This is MHD turbulence simulation, but they look very different. This is turbulence. This is not turbulence. This is just noise. So this doesn't have all of those features that we are interested in, those current sheets and plasmoids. And so that's why we want to run simulations from the first principles. So, and this phenomenon is called intermittency. So this is, so if you hear this word, you can imagine this picture. It's very illustrative. So far, I haven't said anything about particles, almost. So what happens to individual particles? If we trace them, again, this is a very familiar thing for an example. If the particle is lucky and gets here in the area of the magnetic reconnection in this current sheet, current creates the electric field, and electric field that is along the magnetic field if we plot the same region but in electric field projected in the magnetic field, we see strong electric field that can accelerate, accelerate our particle along this electric field until it quits this reconnection region. And that's how the particles are so-called like injected into the turbulence. So let's follow those. For example, we see that in this region that I was focusing on, particles appear. The larger the particle, the more the energy it has. The size is proportional to the logarithm of the energy, Lorentz factor of the particle. So if the particle is lucky, it gets energized. Also, we see, okay, sorry. Let's look at some other particle. For example, this one. This goes in some direction, then it goes in different directions. So those, then it also travels in this. So this is the acceleration the particle undergoes while interacting with different structures of different scales on in the turbulent plasma. So what happens statistically with particles as a whole? So in the end, in the beginning, we have this thermal distribution of the particles of some temperature, and then this beautiful power law tail forms that I was talking about in the beginning. This is very good, and but what happens in principle here is that we can look at the particles, look what particle had accelerated or under the characteristic time of the acceleration in the reconnection area and the characteristic amount of the acceleration, and then we can sort them out in the new population of non-thermal particles, and we see that with time the plasma, the particles heat, but also the non-thermal particles appear that they're responsible for this tail. And I also wanted to say that we have this characteristic energy that particle gains during the reconnection time. And yeah, I just wanted to emphasize what it means on this kind of picture. Each particle rotates around its own magnetic field line. So thermal particles rotate with very small radii. They all exist here on the picture on a very, very small scale. They cannot interact with the turbulent plasma. But as long as they, as soon as they get lucky and get into the reconnection area, they accelerate and jump into energy on like both scales. And then they can interact with these different structures, plasmoids and current sheets, these intermittent structures, and gain energy. And we study this process, how they then climb this ladder, sort of. What kind of interactions? So if we have a magnetic line, magnetic field line, this was proposed as an explanation of cosmic ray synergization in 50s by Fermi, Enrico Fermi. Both of those processes, actually. So we have a particle that moves around the magnetic field line and also meets a perturbation in this magnetic field line. For example, it can be like a bending of the magnetic field line, or it can be like strengthening of the line. And this structure also moves, and the particle, as long as it's like as a bead on a string, it only can move sort of along this field line. It reflects from the structure and gains energy in the process. What is our, so in first principle, we have just a particle and it feels both electric field and magnetic field, and just we integrate this sort of differential equation every time, and we get this composite motion. But we can also describe this motion as separately the rotating motion around the magnetic line and motion along, and probably motion perpendicular to the magnetic line as a drift of the ring itself. And then we can get some complicated maths. This is the tip of the iceberg, and we can, in this description, after averaging and doing all the maths, we can get, for example, different terms that are responsible for different mechanisms, and we want to study what of the mechanisms are more important, what mechanisms are responsible for what. This is the idea after this gyro center approximation. So in this case, this is still like a work in progress. So like coding all this is sort of an ambitious task. So far we only have like our first sort of approximations working. For example, we have one case for this ring being always coming, the radius of the ring at each time step goes to 0. This sort of artificial way to introduce cooling, synchrotron cooling, when the particle moves along the magnetic field and loses energies and emits radiation. But this is sort of artificial. We just put the ring radius to 0 every time. And the first result here is that, for example, we see turbulent behavior again. And this is very interesting and sort of unexpected, probably. We only assume for several, like one kind of drifts that are present in the simulation, and we still see interesting like turbulent pictures, and particles still accelerate even though they artificially, their gyro motion is artificially put to 0. So I think, yeah, in the end, I have this sort of conclusions that we are running our particle in cell simulations to understand accretion flows better and just the physics of the magnetized turbulence. We implement the gyro approximations to study the different processes separately and see what affects what, and to figure out the exact mechanisms of these non-thermal particle accelerations, And this is still work in progress, and we hope to get like simulations with more of those drifts taken into account and so on. Thank you.
Thank you very much, Vlad. So we have time for one question. Please.
Oh, on the simulation, no, it doesn't mean anything. It's just a certain amount of time steps that we keep. Doesn't mean anything.
All right, hi everyone. I'm Tri. I'm from the MIT Kepler Institute, the Institute for Artificial Intelligence and Fundamental Interaction at MIT, and I was a pre-doc here last semester. And today I'm super excited to be back and tell you about my work on how to generate mass assembly history of dark matter halo using generative models. And before I start, I want to acknowledge my awesome collaborators who are Chirag Modi, Aaron Yun, and Rachel Somerville. All right, so let's get started. So first, I want to introduce you to something that we use very often in galaxy simulations, which are merger trees. So what are merger trees? We know that using the hierarchical galaxy formation models, small dark matter halos form into larger and larger dark matter halos, and galaxies are born within these dark matter halos. So the relationship between these halos are usually described using the merger trees. So what is the anatomy of a merger trees? How do you describe a merger trees? So first, you have the root halos, which, for example, in the case of galaxy mergers within the Milky Way context, where you have multiple kind of different satellite galaxy merged into the Milky Way, the root halo would be the Milky Way. And you have the link, which describing the progenitor-descendant relationship. For example, back to the Milky Way case, when the Milky Way actively accreting satellite galaxies just as the LMC, there will be a link between the LMC and the Milky Way. And what is most important for my talk is what's called the mass assembly history, or also the main progenitor branch of merger trees. The mass assembly history keeps track of the most massive progenitors of the merger trees, and therefore has the most significant effect in the formation of the galaxies. So why should you care about merger trees? Why are they important? So you start with, so what you want in the end is you want to study populations of galaxies. You want to study what does my population of galaxies change if I have this physical model or if I have that physical models, and you want to compare that with observations. So our goal is to have galaxies. But n-body simulation, hydro simulation, they are extremely expensive. You cannot just simply run an n-body simulation, run a hydro simulations and get galaxies. So the quickest way is for you to have a dark matter n-body simulation, dark matter only simulations and then you can extract the dark matter halo merger trees out of them, and then you can combine them with semi-analytic models, or SAM, which includes a lot of massive physics, including, for example, gas cooling, star formation, any kind of feedback physics, and then you end up with galaxies. So this is why merger trees are extremely important. So how does astrophysicists normally plant merger trees? So the first way you can do it, like I mentioned before, is you can run an n-body simulation, and then you can use things such as Rockstar to keep track of the halos, and then you can use consistent tree or any kind of tree reconstruction algorithm to basically link those halo into a tree structure. However, this is not very good. Even n-body simulation, even dark matter only simulation is computationally expensive. And because they are computationally expensive, they are limited by resolution. It is extremely difficult to study a wide range of mass and volume in an n-body simulation. For example, you cannot easily study anything from a dwarf galaxies and galaxy clusters simultaneously. And the other way you can do it is you can use a standard Bragg-Schechter algorithm, which model the conditional mass function. But the Bragg-Schechter algorithm, to use them, you have to make a lot of assumptions, and also they only take into account the mass. And we know that the formation of galaxies, depends on more than just the halo mass. So this is not very good either. Projected trees are usually not very accurate. So I want to really stress that generating merger trees is very, very challenging. Like EPS or extended projected trees, they can disagree with simulation by a few factors. So if you look at the graph that I show here, you can see that the extended projected trees, which is the dashed line, and the simulation, and this is the mass as a function of redshift for 4 different mass bin. And you can see that, and this is on log scale as well. So you can see there's a discrepancy of multiple levels between the trees. So this is because the accretion rate depends on the formation environment and also the cosmic matter density, which changes the function of time. So there's a lot of underlying physics going on here. So to solve this problem, we resort to using machine learning. And in this case, we would use generative models. So an overview on analysis, what do we want? Given a root halo, so given the Milky Way, for example, I want to generate an ensemble of mass assembly histories. An ensemble of member channel to branch, because merger trees are inherently random. If I give you a Milky Way in a different location of the universe, they might not have the same satellite or the same formation history. So you want to model the entire population of them. And the other thing that we want to do is want a model that's flexible enough that we can build in all the correlation with the formation environment and all their variables as well. So how do we do it? So for the machine learning framework, to model the mass assembly history, we can model them roughly as a time series, and we can use recurrent neural network models to model them. For ensembles part, we can use generative model, and in my case, I'm going to use a normalizing flow, if you're familiar with that terms, to model the ensemble history. And for the formation, because we use the neural network, we can incorporate any kind of variables into the models. And in our case, I will feed it in the dark matter concentration, which has been found to be related to the formation history of merger trees. So for our models, we have Flora, which stands for flow-based recurrent models for assembly history. All right, so how does it actually work? So at a certain time step, given the input features, which X and T, which T are the scales factor of the current time step and the next time step, and X is our features, which is mass and concentration of the current halo. We feed it to some kind of gate recurrent unit, which is just a variation of the recurrent neural network to extract some kind of learned representation. And because this is a recurrent neural network, it also have a hidden state that's stored every time step and get updated every time step. And this allows it to remember the history of the halo. So this is the feature extraction phase. We will use these features, the learned representation, Z, to model the condition a normalizing flow, which models a base distribution and slowly transform this base distribution conditioning on Z using using change of variables to predict some kind of distribution that we want. Here, the variables that I want is the accreted mass and the concentration of the next halo. And this is the density estimation phase. And during training, I will minimize the loss function, which is the negative log likelihood that I show here. So during sampling, you can sample directly from the output of the normalizing flow from the estimate distribution, and you can modify this output. So because I have accreted mass here, I convert the accreted mass into the mass of the next progenitors, and to some kind of post-processing phase, and this is a generation phase. All right, so let's play a quick game. Can you tell which trees are generated by Flora and which trees are from embodied simulations? So while you're looking at it, I will try and use the time to explain the plot. First, the shaded regions is the extrapolation region, which means that I never train the network on everything outside of z equal 10, like z greater than 10. But the network somehow should be able to, if it's robust enough, it should be able to extrapolate to this region. All right, so if you haven't figured out already, the right one is generated by Flora. But the idea here is that it's extremely difficult to distinguish them as a matter of fact, it's pretty much impossible to tell them eye by eye. The simulation we use is a very small multi-dark Planck simulations. And now I'm moving from individual trees to looking at like population statistic. And the population statistic here, basically I'm showing you, the same plot, just the mass as a function of redshift, but instead of showing individual trees, I calculate the median and the 68th percentile and the 95th percentile middle containment region. And as you can see here, the line by Flora follow the line by very small multi-dark very, very closely. And I plot the residual in the bottom panel. And as a reminder, the shaded region is the extrapolation region. The network has never seen this extrapolation region, yet it is robust enough to be able to capture the population statistics like within them. Another thing I want to show is I want to see if these trees can be used in semi-analytic model in place of n-body trees. So for this, we apply the Santa Cruz semi-analytic model to estimate the stellar mass of each galaxies that arise from the mass assembly history. So each of these dots here you see are like the mass of the galaxies that estimated from the SAM given the initial halo mass on the x-axis. And here I show the 68th percentile and the median of all these data points. And as you can see, again, Flora and very small multi-dark agree to a very high level, and they're extremely consistent. So another thing that you can do with this is you can prop something called the assembly bias. And you can do so by plot the residual of the SHMR or the stellar halo mass relation previously shown in the last slide. And you can see here that it shows correlation with the concentration. So why is that? This kind of implies that there is some kind of order dependency on the stellar mass outside beyond the halo dark matter mass. And this is known as galaxy assembly bias. And again, you can see here that the relation between Flora and the relation of the n-body simulation from very small multi-dark are extremely similar. And this means that Flora trees can be used in place of n-body simulation trees, which is extremely important because it will speed up the analysis of a semi-analytical model extremely fast. Another thing that we do is now we have another simulation, which is called the graph simulation that's run by the amazing Aaron Yoon. And the graph simulation is at very high redshift, and it's kind of like starting at redshift of z equal to 6, but it has very high mass and time step resolution at this redshift. So here I'm pretty much just showing the data, the n-body simulation, and you can see the very small multi-dark trees and the as well as the graph trees. And now what I'm going to do is I'm going to remove all the lines and replace it with Flora. So here what basically happened is that I trained two networks and then I concatenate them together. I trained a very small multi-dark network that you have seen previously, generate them up to z equals 6, and then I train another graph network, another network on graph, and then generate it from the output of the very small multi-dark network. And as you can see, the lines up pretty well. And this shows you that like using this concatenation scheme, you can generate a mass assembly history from z equal to 0 to z equal to approximately 20, which has never done before using n-body simulation. And all of this also have extremely high resolution, has sufficient resolution. You cannot do it like with even with Illustris. If you're trying to look into Illustris or any other simulations at high redshift, they will not have sufficient resolution. But in our case, because we're using multiple simulations and we concatenate multiple networks, we are able to do so. So I will leave you with my summary slide. So in summary, we developed Flora, which is a generative recurrent models to generate mass assembly history on member generative branch of merger trees, and we are able to recover important relations such as the history itself, the stellar to halo mass relation, the assembly bias, and combining multiple simulation, we are able to generate something from z equal to 0 to z equal to 20 with sufficient resolution. And we have ongoing work to tackle generation of secondary branch and as well as condition this Flora on different cosmology to study cosmological dependence of galaxy merger trees. Thank you, and I will take any question.
Thank you very much, Tree. Questions? Please.
Hi, really amazing job. I'd like to know, in your opinion, like taking a look at this extremely powerful extrapolation that you got. So, do you think that normalizing flows are the way to really deal with things that that we cannot see, like these generative models to take like probability density distributions instead of like only one single value points are like the answer to the machine learning starting from now? Or do you think it's like a question of, because you use like your residual neural networks as well together, do you think it's a mix, or do you think it's more related to the problem that you are solving? Sorry if this question is not so easy, but I was really impressed and I really like it to do this question, sorry.
So I think the normalizing flow is very important if you want to like model a distribution, because without normalizing flow, you will not be able to capture the entire distribution. But the normalizing flow here in this case is conditioned on output from the recurrent neural network. So I think both components are optimized simultaneously, and I think both components are equally important. Yeah. I do think the way that I predict this is because I predict the accreted mass instead of the mass of the next progenitor. I think it's very important for the extrapolation process. Yeah.
Thanks.
Other questions? Please.
Hi. I think maybe you already mentioned this, but what are the main applications for generating these detailed merger tree? Like what can we do with like in-body simulation if it's like resolution issue and stuff? Thank you.
Yeah, so with hopefully this answers your question. To the trees itself, the merger trees itself, they are used as an input of semi-analytic models to like kind of like paint, quote unquote, paint the galaxies on top of them. And using that, you're able to like study the galaxy formation process. Let's say, for example, your semi-analytic model has a feedback parameters, and you want to explore the feedback parameters, and then for each of those parameters, you want to compare them with observations. You can't do it like without merger trees or with only a few merger trees, because you don't have the statistic to do that. So you need a lot of merger trees, but even running n-body simulations takes a lot of time. Like even just dark matter only, it takes a tons of time, even months. Yeah, and not including things like hydrodynamic simulation, which take even longer and even harder to explore different like scenario of galaxy formation.
Okay, maybe one final question. Please.
Yeah, this was wonderful. Thank you so much, Tree. I was wondering how easily, this is maybe a naive question, but like how easily can we connect the mass assembly history to other things that influence the assembly history of a galaxy? So like the star formation history, all these other parameters we also care about when we're talking about galaxy formation and evolution. How much can we connect, those two things in the future?
Yeah, so that's an awesome question. So the first thing we have to do is we have to move away from just mass assembly history and generate secondary branch or other branch as well, other sub-branch of the tree as well. I have plans to do that using either graph generative models or with the current recurrent scheme that currently applied to this model. If you can model the branching probabilities of the trees, then you can still recursively generate the entire trees with only one recurrent models. So to go from that to other properties of galaxies such as star formation, I would refer you to a work of Christian Jefferson. He used a graph neural network applying on merger trees to basically predict semi-analytic models properties, predict these kind of properties, as well as studying the link between different variables. So I guess we can chat later and I can point you to that paper. Yeah.
Hi everyone, my name is Sheila Sager. I'm a third-year PhD candidate at the University of Florida, and I just am finishing up my pre-doc right now at the CCA. I'm working with my advisor, Adrienne Price-Whelan, as well as my PhD advisor who's visiting today, Sarah Ballard, on the ages and metallicities of M-dwarf planet hosts. All right, so I'll start by introducing kind of the motivation for this project. So my primary interest is exoplanets, particularly small exoplanets around M-dwarfs. M-dwarfs are by far the most common star in the Milky Way, and there's a few reasons why they are so interesting to us as planet hosts. One of the main reasons is that they've emerged as the predominant host to small rocky exoplanets that may or may not be in the habitable zone and in similar size to our Earth. There's a couple of reasons for this. One is that M-dwarfs, like I said, are extremely abundant. About 80% of the stars in our galaxy are M-dwarfs, so statistics is on our side there. They also host small rocky planets at the highest rate, actually higher than even FGK stars like our own sun. Planet occurrence is exactly what it sounds like. It's the rate at which planets occur around M-dwarfs, and this is really our window into understanding planet formation and habitability from a demographic standpoint. And right now, it's best understood as a function of planet properties, such as orbital period and the planet's radius. So really what we want to do in this work is to understand planet occurrence through the lens of the stellar host properties for M-dwarfs in particular. So we want to understand how these stellar host properties affect how planets form and evolve. So here we're really asking a causal question as opposed to a question of correlation. Do planet occurrence and orbital dynamics evolve with age and metallicity, or rather do age and metallicity cause planets to exist, form, and evolve in a specific way? So this question doesn't just come out of nowhere. We know that metallicity is correlated with planet occurrence and size. We've known this for decades. It was first proposed by Fisher and Valenti in 2005, almost 20 years ago. And metallicity has also more recently been shown to correlate with orbital eccentricity. So this is kind of the dynamics, orbital dynamics side of things. So our goal here is really to untangle the relationship between stellar age, metallicity, and these orbital dynamics. So you might know that metallicity and age are related. They're completely intertwined properties. So we really want to kind of break them apart, which is not easy to do, right? If you saw me give a lunch talk a few weeks ago, I might have shown you our work, mine and Sarah's work on finding the orbital eccentricities for a bunch of M-dwarf planets. So orbital eccentricity is really the dynamical property that we're most interested in right now. So I'm going to give you an example here about of one of the questions we might be able to answer using these three pieces of information. So we might investigate a nature versus nurture hypothesis for planet evolution. Say we have two stars, star 1 and star 2. We have metallicity and age information for both stars. Say that we know the metallicity is pretty much consistent between these two stars, but we know that their ages are inconsistent. One is younger and one is older, right? If these planets are, or if these stars are both planet hosts, and we observe the same planetary architectures around stars 1 and 2, so by this I mean orbital eccentricity, mutual inclinations, just the shape of the orbits around the star. If they have very similar planetary architectures, we might say that, well, metallicity is the predominant factor in determining system architectures. These systems might be locked in at birth, and long-term evolution is not as significant because these stars are different ages, yet they have the same types of planet dynamics. Or we could go for a nurture perspective. If we see that stars 1 and 2 have very different planetary architectures, we might say that, well, age, long-term evolution is far more important in determining these system architectures. They might all form kind of the same way and evolve into something different depending more on their age. So this is a tall order. I realize that because measuring ages for M-dwarfs is extremely, extremely difficult. You can't just look at an M-dwarf and try to even guess how old it is, as we all know, because their lifetimes are extremely long. They change so little throughout their lifetimes. But there are a couple ways that people have figured out how to extract ages from these M-dwarfs. One of these ways is by using gyrochronology. We know that stars' rotation periods change throughout their lifetimes, and stellar rotation periods are observable through, Kepler transit light curves, ZTF, time series data, essentially. Or kinematics, so we can really understand how the stars orbit within the galaxy. And drawing the orbit of a star throughout the galaxy reveals a lot about the star, including its age. So we're really focusing on kinematics throughout this project, though this will almost certainly yield less precise individual ages for each star. It will likely be more useful from a population perspective because we have so much more kinematics data than, time series light curves for M-dwarfs. So I want to talk about how we're going to do that. You might have heard of something called the age-velocity relation or the age-velocity dispersion relation. Essentially, we know that older stars tend to have higher velocity dispersions out of the galactic plane, so in the z direction. So this could be due to a couple of reasons. They may have formed at higher galactic latitudes at earlier times and just stayed in those orbits, or their orbits may have been perturbed over time, with older stars having more chances for their orbits to be perturbed in the galaxy. In any case, now with Gaia kinematics data, specifically Gaia DR3, we are able to fold that in with a mass model of the Milky Way galaxy and actually draw out the galactic orbits of stars, essentially. So I'm showing you here a schematic, this blue orbit, which this red star is going around, and I've labeled the z direction. So we do this using software like Gala, which my advisor here at CCA, Adrian, wrote. So even though my primary interest is in exoplanets, this is one reason I was really excited to work with Adrian, because his expertise is in Gaia data, galactic dynamics, which is really key for this. So what if we have a case like this, where we have two stars almost indistinguishable on the same orbit, but they exist at different times throughout that orbit. We're observing them at different phases. So this top red planet might have a small vertical velocity at this point in time. The bottom star might have a larger vertical velocity because it just happens to be near the galactic plane throughout its orbit, but really these have the same orbit, so we should extract the same age from them. How do we get around that? We use something actually called the vertical action instead of something like the velocity dispersion. So I'll explain what that is. The vertical action, we call it JZ, is an integral of motion equal to the integral of the vertical velocity versus the vertical position over the entire orbit. So what does that mean? I can kind of describe it like akin to a spring constant for a harmonic oscillator. JZ represents a summary of the system's energy even when the system's motion, this stars orbiting the galaxy, changes over time. So just like how a mass on a spring would change velocity and position over time, but have the same spring constant, JZ would label this specific system by its energy, no matter which phase you're observing it during. So these two stars, even though they're on different phases of the same orbit, they would have the same JZ. So we use JZ in favor, or instead of like something like a velocity dispersion, because we think that because we can identify cases like this and draw out the same age from them, we should get a better correlation between age and our kinematics information. So unfortunately, though, we can't just take JZ and like say it's a proxy for age. We don't really know to that degree how this kinematics information translates into age. So we really need a calibration sample, a large sample of stars for which we know the ages to calibrate a model to translate vertical action into age. So we have a couple of choices for this. One, we might use Main-Sukens turnoff and subgiant branch star ages. So these are stars for which the ages are relatively precisely known with stellar isochrones. Or we might use something like a sample of gyrochronological ages, which is what I talked about earlier. Both of these are good options. We have tons of stars in in various samples from each category. And we would combine one of these with the vertical action. So we would take our sample of stars with known ages, calculate the vertical actions for all of those stars, and describe that relationship with some kind of model. So this could be a hierarchical line or polynomial or spline, or something like a Gaussian mixture model. I would say that we probably tried tens of different models. I'm going to talk you two of them in specific during this talk, but we had to make a choice of models. So, and also we ended up using main sequence turn-off star ages for what I'm going to show you in this talk. Okay, so like I said, we have a sample of stars for which we know the ages. There's some error bars on those ages. We calculate vertical action, and we would plot that sample on this parameter space and then fit a Gaussian mixture model to those points, which is essentially what I'm showing you here. And this is so that we can, like I said, construct a model where we can use any star's JZ, which can be just calculated from Gaia data, to predict the age. So what that means is that we can make a plot like this, where I have age here on the x-axis, and these are just an array of probability distributions, each line corresponding to a different test value of vertical action. So you can see that, or log vertical actions. So you can see that smaller log vertical actions correspond to a younger age prediction, and vice versa for older age predictions corresponding to higher JZs. So this makes sense, all good, right? Well, you may have noticed that we are not trying to find the ages of main sequence turn-off stars. If we were, we would not still be working on this probably. We are trying to apply this to M-dwarfs, and we kind of made peace with that by saying, well, we don't think the age-JZ relation, because it's dependent on galactic kinematics, we don't think it's necessarily strongly dependent on the mass of the stars. However, what is dependent on the mass of the stars is the number density on the age axis. So you can see what this means. Our Gaussian mixture model is going to fit that overdensity of stars around 10 gigayears, which makes sense, they're main sequence turn-off stars. But what that's going to do is pull our age predictions towards that 10 gigayear kind of bubble. And we don't want that because we don't think that M-dwarfs have this overdensity at 10 gigayears. So how do we get around that? We ended up fitting a hierarchical spline model. And so this spline model, we fit this model that describes this trend, this age versus lon JZ trend, along with the intrinsic scatter of points and also the number density. So I'm not showing it here on this plot, our fit of the number density, but that's because we wanted to fit that as a separate parameter so that we're able to marginalize it out. We're able to apply the spline model to a separate sample of stars while making our own assumptions about the number density of stars on our age axis based on whatever sample we're interested in at that point. So another way to say all that is that on the left, we believe the slope of this line, but not the relative densities. And the right hand just removes the relative densities. So now we can make a plot like this using our hierarchical spline model. It's the same idea as the plot I showed you before, where I have several test values of log JZs corresponding to age predictions. So this is really fun, and we don't get this problem then of all the age predictions being pulled towards around 10 gigayears just because that's where the highest number density of our calibration sample exists. And I think this plot is really exciting. This is kind of the same idea as what I just showed you, but instead of just test values of lon JZ, these are vertical actions that are from real Kepler M-dwarfs that I calculated using this Gaia data. And we can really do this for any stars, any M-dwarfs, or probably FGK dwarfs that have Gaia parallax, proper motion, and radial velocity. So there's a ton that we can get age predictions for. And of course, the tails are quite wide, but that's what I mentioned about kinematics. We won't get very precise individual ages, but we have so many of them. So I'm going to talk very briefly about this last part of my project. It was not nearly as analytically taxing as what I just talked about, so I kind of just have one slide on it. But I want to emphasize that though I'm talking about it for a shorter time, it has equal weight as the ages when it comes to interpreting these results, like I talked about in the beginning. So we also calculated stellar metallicities, and we did this in a way that only requires us to use Gaia color and magnitude information, which is really great. We don't need spectra of every single M-dwarf. So the way we do this is by following a method that Jason Dittman first published, I think in 2016. We essentially take Gaia BPRP color and absolute magnitude and draw this color magnitude diagram where each of these dots is an M dwarf, a Kepler M dwarf, and we fit a spline to the middle of the model. And we say, well, that spline represents the main sequence at average metallicity, and the distance of each star from that main sequence at average metallicity represents the metallicity. So this method has been calibrated and compared with spectroscopic metallicities for M dwarfs in particular. And that's one of the reasons why we're using this method instead of, for example, using Gaia XP spectra, because there are other problems when it comes to very, very low mass stars. And this method has been specifically calibrated in regards to low mass stars, at least by these two works. So we also have metallicities essentially for free for a ton of Kepler M dwarfs, which is really exciting. So next steps. That's interesting in its own right, I think. I think it's great to have even, wide age predictions for all these stars. But can we draw out an age metallicity eccentricity correlation, which is what I really, really want to do? Not yet, but it's really because our sample size is limited on the eccentricity front. So fitting transit light curves, if you've done that before, you might know that it's extremely computationally taxing. And we have eccentricities for about 150 planets so far around Kepler M dwarfs. So what we'd really like to do is calculate eccentricities for lots more planets, so test planets, K2, and maybe expanding to other spectral types. We're not sure about that yet, but I would like to see where that goes. As an aside, I think it's really, really amazing that in 2022, our sample size is limited on the front of how many high signal-to-noise transit light curves we have. That is incredible. But also, we might leverage a calibration sample of gyrochronological ages. Along with these isochrone ages that we're using, we're still kind of playing with that. And finally, within a Bayesian hierarchical framework, we want to see if we can tease out an underlying age, metallicity, eccentricity relationship, and maybe mutual inclination as well, at a population level for really all, including all of the planets that we can get our hands on, as long as we have these three pieces of data for them. Okay, so I will leave up my conclusions here, and I also want to thank my group at UF who's visiting. A bunch of my colleagues are in the audience here, and also Lucy Liu, Jiayan Dong, and Nora Eisner for really interesting conversations that helped contribute to this project. Thank you, and I can take questions.
Thanks, Sheila. Questions? Please, Tree.
Hello, is it working? All right, I have a question. So whenever a star passes by a dark matter substructure, like the dark matter substructure can deposit some energy into the stars and change the action. I think. Could you comment on how, how this analysis will be affected by dark matter substructures?
Yeah, that's a really interesting question. I'm not gonna lie, I'm not super familiar with dark matter and how that might affect things like galactic dynamics. My background is in exoplanets, so I'm just breaking into this. But what I can say about that is that depending on the scale to which dark matter might affect, these large populations of stars, like I mentioned, we have vertical actions, and we've calibrated our JZ age relation on so many stars. So our calibration sample has on the order of 10 to the 5 stars, maybe a couple, 200,000-300,000. So my initial hope is that because our sample size is so large, that that effect is kind of washed out. But that's a really interesting point, and I would have to check on that because that hasn't occurred to me. Thank you for bringing that up.
All right, thank you.
Thank you all for staying until 5 p.m. on a summer afternoon. I know that everyone's really excited to hear about even more science, so I'll try and keep people awake.
Cool. My name is indeed Arjun Savell. I'm a rising fourth year now geek at the University of Maryland College Park, where I work with Eliza Kempton. But today I'm here to talk about the work that I did as a pre-doc last fall with Megan Bedell and all the wonderful collaborators below. And during my time at the CCA, we were really interested in digging into the uncertainties that are inherent in this technique called high-resolution spectroscopy. It's really new, really exciting technique. And over the course of our work, we uncovered a couple really intriguing biases that I'm going to be digging into. But zooming out just a little bit, why do I care about exoplanets at all? I have my training as a theorist. So usually I think about exoplanets from the context of the physics. I want to build more complex models. I want to help observers interpret their exciting new data in exciting new ways. So I want to think about exoplanets' climate. I want to think about condensation states, whether there are clouds and things like that. And I want to think about chemistry as well. But as I was coming to the CCA, I wanted to bring this theorist knowledge with me, but really what I wanted to do was touch grass for the first time in my life. And what I mean by that specifically is that I wanted to build realistic simulations. I wanted to not just have living in theory land over there, these really complex physical models, but have realistic noise-inclusive simulations. And to motivate why we need to have more realistic simulations, I'd like to talk about exoplanet spectra in general. So exoplanets can be self-luminous, they can have heat from formation, it's a very chaotic formation they have, and they can also have heat deposited by their stars. So they are intrinsically luminous. Spectra are a great window into composition, into climate chemistry, all the stuff I'm interested in. So let's take a look at some spectra and see why I like them so much. So that's not much of its spectrum. Nothing against Spitzer here. Spitzer's done a lot of great work. We love Spitzer, but it's clear that, at least on the resolution axis, we can do a little bit better. Okay, so now we turn to Hubble-style resolution. We're getting a little excited here, but I think rumor has it we just launched a $10 billion spacecraft that maybe can help us do a little bit better on that resolution front again. And wow, JWST is looking pretty good. Thank you, JWST. And in the audience, you might be thinking that this is about as good as it gets in terms of resolution. But if you're willing to give up your dreams of going to space, you can build a very fancy, vacuum-sealed, heavy spectrograph on the ground. Wow. That's a lot of wiggles. So me, as a naive theorist, I've never seen a data in my life. I look at this graph and I say, wow, I absolutely want to crank up the resolution always and forever ad nauseum. Can we do that? Let's find out. I'm especially intrigued because when we crank up the resolution enough, we get a whole other quantity basically for free. Not only do we get to see these spectral features, we get to see their Doppler shifts over time. So this planet, it's not stationary. It's whipping around its host star, right? So the emission and absorption originating from the planetary atmosphere is going to blue shift when it's coming toward us and red shift when it's moving away. And this is especially exciting because there are other things going on, of course. It's very rare that we're actually spatially resolving the exoplanet. So we got other junk in there, right? We have the tellurics, that's the absorption by the Earth's atmosphere, and we have the stellar spectrum as well. But the star is not going to be moving very much over the course of a single night. And the Earth, I hope, doesn't have an atmosphere that's moving away from me at 10 kilometers per second. So those other components are going to be relatively static. And you have this planet that's just whipping back and forth. And if you have good enough resolution, you can even ascertain the speed of winds within the planetary atmosphere. So again, I see this naively. I'm like, wow, I want to crank that resolution all the way up. But there's a bit of a wrinkle, right? We still need to get rid of those other spectral components, even if they're not moving. We need to get rid of them somehow. And here's a fun little plot where we have the frames, the number of frames, so successive exposures on the y-axis, and on the x-axis, it's wavelength. So we see all of these other spectral components, they're just schlump, they just kind of go down. There's not much time variation there in this assessment of the situation. And if we want to get rid of all of these very, very strong spectral features that aren't from the planet itself, we want to get rid of, to reframe the question, these high variance with respect to wavelength, bits and pieces, components. Luckily, there's a whole set of algorithms related to principal component analysis, PCA, that can help us with this problem. So PCA is going to identify these regions, these components that have very strong spectral variance. And once it identifies that, we can basically divide it out. So this sounds great, right? We're going to divide out the star, we're going to divide out the tellurics, and everything's going to be great. We're going to have a beautiful planetary spectrum just like before. But we end up with junk. It's very sad. It is very, very sad. So there's a huge caveat here, right? We need to do one extra other thing, at least, in order to eke out the planetary signal. So we need to resort to this thing called cross-correlation analysis. So we have all that junky data, right? I'm sure that there's a planet in there somewhere. People like Chris have spent their lives planning all these RV observations to make sure there's a planet there. So we know there's a planet there. We have to get its atmosphere. So what we can do is we can take our data, we can take a model that we presuppose is a great representation of the planetary atmosphere. We Doppler shift it over our data, multiplying as we go. And that function should be maximized at the Doppler shift where our model best matches the data. And if we see a big lump over there, voila, that means we've detected the planetary atmosphere at high confidence. So that's great. That's our second wrinkle. And now with all of our wrinkles hopefully solved, we can now look at the glorious history of high-resolution spectroscopy. So this started back in 2010, so relatively recent as far as things go. I was like in 6th grade, still learning to write my name. And over the years, as more instruments come online, as the techniques become a lot better, as grad students like yours truly get roped into this whole business, we see an explosion in the number of detections. So that's the y-axis over here. You got your ions, you got your metals, you got your molecules. And on the x-axis, you have all these different planets that we've found all of these different things in. It's very exciting. And me, of course, I had to jump on the WASP-76b hype train just like everyone else. So if you want me to not shut up about a planet, ask me about that one. But the idea is that, yeah, 2010 seems like a long time ago, but it's not all that much time compared to the fundamentals of exoplanet science, fundamentals of spectroscopy in general. So we're still working out some of the kinks with respect to how to interpret all of these things. In particular, we only got really rigorous parameter inference in like 2018 or 2019 for this data type. So there's still a lot to be worked out here. And in particular, I think this is probably like the 7th black box that has been shown today. But once again, we have a black box where there are a lot of signal processing and data analysis techniques being applied. And it's not entirely clear how all of these different approximations, different techniques imprint themselves upon our data. So as I mentioned before, we perform PCA. What does that do to the planetary signal? Don't really know. We have our tellurics. We've made this excellent approximation that they don't do anything funky over the course of a single night. But anyone who has gone to a telescope can verify that the atmosphere does not always stay perfectly still. There's a planet in there. I want to get inside this black box. Additionally, there are other varying spectral components that we have not yet considered, right? The spectrograph itself, is it fully stable? Not all of them. Noise exists. What does that mean? So as I came to the CCA, I wanted to think a little bit more clearly about some of these concepts, and I was able to reframe these into a little bit more concrete science questions. So how do these data-driven methods that we've resorted to actually affect the data? Can we, if we assume that there's some time dependence to this telluric absorption, can we incorporate that into our simulations? Again, I'm a theorist, but it's really hard to simulate that time dependence from first principles because there's a lot of competing factors going on. Noise, we understand it well enough. Photon noise, shot noise, we can well describe it with Poisson statistics, sure, but that understood framework of noise, how does that percolate, trickle down all the way through to our inference at the end of the day? And finally, if we accept the fact that unfortunately observations are not perfect, how do we quantify that measurement uncertainty and how do we, even better, simulate it? So the goal of this whole study is to try and approach this problem from a forward modeling perspective. I take all these complex aspects of data analysis, etc., and I simulate them on a computer like a good theorist, and I see what happens at the end of the day. See if I recover these planetary signal that I input at the very beginning. So I'm just going to briefly walk through this pipeline. It's maybe my favorite part because there's a lot of color on this slide. We're just going to start off with the planetary spectrum. So the y-axis, again, is just flux, whatever flux units you want, just pick them, choose them. And on the x-axis is the wavelength. So we see all of these wiggles, the wiggles that are the intriguing thing to me at the end of the day. The first thing we have to do is Doppler shift these lines properly, because again, planet whipping around its host star, we want to include that. So, spectral traces. So we see these lines actually shift over the course of the observation. This is the time-dependent thing over the course of a single night that we are most interested in. Then we slap our star right on top, and we can immediately begin to appreciate why this is a tricky problem. By eye, I challenge anyone here to pick out where the planet is in that combined trace. Even though the star isn't moving very much, it is just dominating because it is emitting and absorbing a lot of its own light. Then we have the telluric contribution, and things begin to look even worse, right? Whole pixel channels are just gone, can't use them. Finally, we incorporate the instrumental response, so the Blaze function, wavelength-dependent throughput, and any spectrograph instability. We can include that at that point. Finally, we do all the principal components analysis, cross-correlation magic, and voila, we get kind of a blobby-looking thing. So the takeaway from this blobby-looking thing, 2 different velocity parameters, and we should see the biggest blob right at the intersection of those 2 dotted lines. That's the expected velocity of the planet itself. And we do see a blob. That blob is at 20 sigma. If you want to ask me why I found a 20 sigma blob, we do have 5 minutes of Q&A. So now I'm going to go on to our results. We built this pipeline. We want to answer these questions. What's going on inside this black box? We have 2 corner plots that I'm actually not going to subject you to. We're not going to go through 30,000 rounds of corner plots at the end of the day on Friday. We're not going to do that. I will show you like 3 different slices of it, though. Basic results of this whole thing is that, yes, this technique works, which is great because people have been doing it for 10 years. So when we don't include a pathologically varying atmosphere, when we don't shake our spectrograph back and forth, things look pretty good. So this is our basic parameter inference. If you see circles, that's great. If you see ovals, that's degeneracy, but that's probably fine. Don't worry about it. These are 2 velocity parameters, as I mentioned before. And the third one over there is a scaling of the planetary atmosphere, which people often leave as a free parameter when doing these types of inferences. So let's start answering that first question. Things look nice at first, but what happens if we start changing those tellurics? First, I'm going to do a brief segue, talk about how we simulate varying tellurics in a cool data-driven way, because CCA, data-driven stuff. And the way that we did that is by stacking a bunch of standard star observations. So observers for this type of observation, often at the beginning of their night, they will look at some A star that doesn't have a lot of spectral features, they hope, aside from Balmer lines, which they can get rid of. And they say, okay, well, all of the lines that I see are just the Earth's atmospheric absorption. Cool. So they then use that to calibrate their later results. But we took those calibration exposures themselves, stacked them all together, and performed PCA on them to see how those telluric standard star observations vary as a function of time, and vary as a function of air mass. So these are the eigenvectors, or eigenvalues rather, for all of those different eigenvectors, and how they vary as a function of time and as a function of air mass. Then we can reconstruct what the tellurics look like along just those individual dimensions. You can see that as you crank up the air mass, as you'd expect, the absorption becomes deeper. You look through more of the Earth's atmosphere with your telescope, you have a lot more absorption. And the cool thing about the time dependence is we found that some lines are going to be relatively stable over time, whereas others exhibit some seasonality on the order of days, weeks, months. So now we include that in our simulation. What do we find? When we include that time-varying telluric signal, some of our parameters become very biased. I'm not going to get too much into the nitty-gritty, but what I will say, look at that top left box. The top left box, there is a huge bias toward the left edge of the prior for, that's the temperature of the atmosphere. Why is the temperature of the atmosphere so far biased toward the left edge of the box when we include this time-varying tellurics? Well, when we were performing our PCA, we assumed that the telluric absorption was constant with time. So that means when we include a time-varying signal, PCA can't get rid of it. So there's leftover stuff in the atmosphere, rather in the data set. Now that scaling factor, 1, 2, 3, third column, that scaling factor wants to use the planetary spectrum to compensate for those extra residuals. But that scaling factor is degenerate with other parameters of interest. So it tries to stretch and scale the atmosphere and does an okay job, but it has to do so in really funky ways that mess up our inference about the atmosphere at large. When we include noising data, things get even funner because we can now get false positives. And that's exciting for me, and maybe a lot less exciting for observers. But what I hope this result means is that we can set more informed detection significance thresholds for people. So I showed that plot before. We had 1 billion different detections, and hopefully studies like this can help inform people, inform the community at large of what constitutes a signal at the end of the day. I'm going to speed through this real quick and just say, when we include noise as well, our inferences about the gases in the planetary atmospheres get really messed up, but with the velocity parameters behave somewhat nicely. And I can talk about that more in the Q&A. Conclusions, in large, this technique works pretty well. That's great. When we include the photon noise, that again, we well understood, but we didn't understand how it affected our inferences. We can bias our gas parameters, but the velocity parameters are more or less safe. And finally, when we vary the tellurics a lot, we can bias our temperature pressure parameters in a very, very sad way. Alarming, but also exciting for me because I wanted to see a result. And I will now take any questions.
Thanks, Arjun. Please.
Sure, great talk. So you mentioned that one of the complications with, making the inference when you have time varying telluric lines is that your PCA assumes that your telluric lines are, constant in time. Is there a way to not make that assumption and then get better results? Like, is that, more of a charge to the observers, like, hey, figure out a way to, include time varying telluric lines in your, in your principal component analysis, or is that kind of hopeless because it's, because of how PCA works?
That is a great question. So the way that PCA is performed in this context is it assumes that in order to back out what the varying components are along the wavelength axis, it uses all the spectra along the time axis. So it needs all of that, as currently implemented, to be constant in time. That being said, I can think of a couple hacky ways to incorporate some time dependence. For instance, breaking up your exposures into like groups of 3. So you perform PCA here, here, and here. And maybe then you will be able to back out time-dependent components in as much as you are allowing yourself to perform PCA n number of times. So that's hacky, and there's probably better ways to do it that allow some smooth joining of the telluric signal over time. But yeah, I think that one really great way for people to incorporate some time dependence in there might be through some more advanced PCA-ish approach.
Yeah, Handler?
Okay, there we go. All right, I'll bite. Tell us about the 20 sigma bump.
Yes. So the 20 sigma detection. So this, I've been scratching my head about it for a while, and I was really worried that I was super overestimating things in a way that was wrong. But I think I'm overestimating things in a way that is okay. And what I mean by that is that the way that we assess our detection significance is through this cross-correlation function, right? And when I'm doing a simulated cross-correlation function on simulated data, the model and the underlying data are going to have perfectly matching line profiles. But in reality, there's a bunch of missing physics that we're not including when we're just comparing to a data set. Atmospheres, for instance, are 3-dimensional, and we don't include a lot of those assumptions here. So I believe that the reason that I'm getting such strong detection significance is because I have perfect template match. So I'm going to punt that to a later study when I investigate otherwise. Yeah.